Hello. Hello. Yeah. Good. Okay, so good morning. Welcome to this session. I feel the pressure of collectively waking all of us up. So yeah, I mean, in case you haven't woken up, I hope that I'll not be boring, that I will further put you back to sleep. But anyway, so this talk, this chronicles the journey that myself and the security researchers of our team we took while we were trying to understand and evaluate the security practices that are happening in Zephyr and how much that is working and if there's any need for improvement or not. So before we go into this, just give a little bit of background of myself. I have been doing static analysis, bug detection, and bug fixing for almost all of my life, about 20 years now. I like to think that I don't look that old, but apparently I am. I've been around and seen a lot of these bug detection tools evolve and mature and where they are right now. Specifically, the work started from my PhD years at University of Illinois at Urbana-Champaign. And my PhD thesis, it focused on asking that question, and it was the first work that asked that question, why stop at detecting bugs? Why can't we also automatically fix bugs in the first place? That was back in 2008, 2009, so quite a long time ago, before any of these LLMs or any bug fixing capability. Actually, bug fixing capability is still not there. But that's where it asked the question. Then I went into academia. I did a lot of research on how do we build tools for automatically fixing bugs. Specifically, I focused on C code. So in 2012, my students and we wrote a paper that was looking into a general purpose problem in C code and seeing whether we can build a tool to fix that problem. And we were focusing on 4 kinds of integer related issues: integer overflow, integer underflow, integer sign mismatch, and integer width mismatch. So 4 of these kind of issues, and can we build a tool to detect and also fix those issues? And that was kind of the grandfather of Open Refactory, which is my company now. But that particular tool or that particular research work was identified as the best computer science research in all disciplines of computer science in 2012. And this was my student and I, we were awarded at the Turing Award ceremony in 2013. So that was like the start of building tools. And then I moved into industry. I worked at Coverity, which is the leading bug detection company in C++ space specifically. But in general, it's a very prominent company, now part of Synopsys. I worked there for a couple of years. I had first-hand experience of the way the C++ tool is built. But at the same time, I was more focusing on, or my team was more focusing on, we were bringing the JavaScript capability into market and also Android bug detection tools. So those were my primary responsibilities. But I know underlyingly like how the stack works and and how the detection algorithms, et cetera, work in order to detect the bugs that Coverity does very well compared to the rest of the market. And then I started Open Refactory. We received an award from the National Science Foundation to take our work that we were doing back in the academia into industries, and we started building a C tool because that was what our expertise was. We built a tool, but then we ran into some product market fit issues. That's a separate story that I can tell offline at some point. But long story short, right now, so our product is called Intelligent Code Repair. Right now, we are focusing on Java, Python, and Go. And this year, we are again building a C 2.0. We already have a C 1.0 that we don't sell from our company at this point, but we are building a C 2.0, and that's how kind of all of this work or the planning of the talk started. And we're also working on Rust right now. So at the end, near the end of the year, we're going to bring tool. So just one more plug about Open Refactory. What we are doing is we are identifying the fundamental problems in the bug detection tool space and trying to fix them. And specifically, there are 3 problems. There's the bug detection tools. They don't find the really hard ones. They find a lot of stuff, but they don't find the really hard ones for you. The classic story is Coverity was used in the OpenSSL stack or CI/CD pipeline between 2012 and 2014 when the Heartbleed bug was introduced. Or no, it's a bug that was introduced, and then eventually when it was detected and catastrophically blown up out of proportions. But it was there all along. It was scanning and never finding anything. Then there is the false positive issue, that the tools generate a ton of false positives. And I'll show some of those examples in this talk later. At the same time, as we discussed, that the current static analysis tools, they all stop at detecting bugs. But I mean, we are here, AI is beckoning on us. Even without that, our computers are computationally much more powerful than we were in like 2008 when we started asking I started asking the question. So it's almost unconscionable, like why don't we have tools that can also automatically fix these bugs for us in some of the cases. So that's what our product, Intelligent Code Repair, is trying to solve. We are finding more critical bugs. We are also doing that with dramatically low false positive. We have less than 5% false positives on benchmark tests compared to whereas the other industry tools, they give you between 70 to 90% false positives. So 10 bugs that they identify, 9 of them are probably wrong. It gets better for some tools, of course, but that's like the other end of the side. And then we are the first tool in this space that also is able to automatically synthesize fixes. So for all the bugs that we detect, about 50% of the cases, we are also able to automatically synthesize fixes. And right now, this capability, again, is available for Java, Python, and Go. We are building the C tool, and when it is there, we hope that these open refactory promises will be reflected in there as well. But before we go into that, just about the finding more critical bugs. So in 2014, when Heartbleed came out, at that point, my students and I, we already moved on, and we wrote another paper, this time also building another tool that is focusing on these buffer overread and underread vulnerabilities. This was already published at that point. We had a prototype tool that's going, and we were wondering, okay, there's this big vulnerability that came out in OpenSSL. Can we detect that? And we were not only able to detect that, we were also able to fix that. That's where our capability was at that point. And when we go back again and build the tool, again, we want to bring that particular aspect. So we were there in the academia, and I didn't know how to marketize this thing and such, because we were just interested in writing papers and solving theoretical problems of the world. But here I am right now trying to take everything or all of these lessons that we have learned from the academic research, theoretical research, very passionate stuff, but then how much of that can transport into market and be useful for all of us. So also a little bit of background of what we do in Open Refactory. We are right now working on scaling thorough security audit and scaling that to a large amount of projects. And the problem here is the tons of false positives that the existing static analysis tools generate. So if we are scanning, let's say, 100 projects, and each one of them is getting 100 extra false positives, that's about 10,000 false positives. And if we take 10 minutes of time to triage a bug to identify whether it's a false positive or not, that's about 100,000 minutes, a lot of time. And so clearly that doesn't scale well. So how can we scale security audits and do a lot of that? So right now we're working with Alpha Omega and Linux Foundation and Python Software Foundation. We had a bigger scope before, but now we have narrowed down the scope of work. We are focusing on the top 2,000 Python open source projects in the PyPI library based on the number of downloads in the last 1 year. And our mission is very simple. We want to scan those projects, identify if there's any bugs in them, report it to the maintainers, and then occasionally provide fixes because we can, and then also work with the maintainers to get the problem fixed. So go the entire mile of delivery for that. And so specifically because there's bugs everywhere, but then some bugs are more critical than the others. So we are focusing on just 32 different kinds of critical security problems. These are identified by the CWEs, also the EOSS list, and so on, as in what are the critical bugs in that space. We're just concentrating on that, not bothering with the minor like bugs here and there. We sometimes report those, but that's not the focus. This particular work is looking at that. And so in the last 5 months, we had about 350 bugs that we detected, 120 of them security related, 40 of them high severity. About 60% of the bugs that we reported already got fixed, accepted by the maintainers and got fixed. So what this has shown that we can take the work and do that at scale, and do a whole lot of good. And so several CVEs, et cetera, have been assigned and are in process of being assigned, and so on. So that's the work that we were doing. So I gave a talk at the EOSS summit in Japan in December about this work. This was just the start, so we were only about a couple of months within that. I was sharing the results. So Kate Stewart, who is one of the champions of Zephyr project, she was there. She just finished her keynote. It was also another early morning talk. I don't know whether they feel like I'm very energized and get all of you guys wake up. So they scheduled me for early morning talks. So Kate Stewart, she just gave a keynote and just came after that to my talk. And so she was very interested about what we are doing, whether we have any plans working with C. And yes, we were thinking of doing or going into that space. And so the plan was, okay, how about we project at this point and basically, and it works for us as well, because from our side, we are looking for feedback from the community or understanding from the community. I've been working on C, as I mentioned, for long time ago. So I have a general understanding of what bugs are more important for the C developers, but things may have evolved. I haven't looked into C very closely in the last 6 to 8 years. And things could evolve. So it would be good to get feedback from our side, from the Zephyr community. And one way of getting feedback is to just look into the audit process, look into the process of what are the tools that are being used by the Zephyr community for detecting these security bugs, and are they working? What kind of bugs are getting reported? What kind of bugs are getting fixed? Is it any different from what we have seen before or has evolved, and so on? So that was naturally also very interesting from us, and we were not. So we, based on our plan, our C product is going to be coming later in the year. So we wish that by the time this talk happened, we would have some operational version of our C tool and see how that worked. But that was not part of the plan. It was more about just giving a thorough look, because we also do the security audits in the other spaces and so on. Give a thorough look about what is happening in this part of the world and how are things working. So that was kind of how this talk was planned back in December. Then obviously went to the CFP process, etc. What is interesting was in October in Zephyr version 3.5, code checker was also introduced, and that was it was one of the main things. And then there's this push towards more security scans or more actionable items coming out of the security scans, and whether they're useful or not. So that kind of questioning, retrospection is happening in the community. So we thought it's a good synergy. So let's have a look at that. So that's basically how the talk started, what my background was, and then how we went through this. So here's a plan of this particular talk. We use the term root canal. This is a term that is borrowed from code rewriting or refactoring literature, where I come from. Where we are rewriting code to fix problems. So in refactoring literature, there are two terms that are being used. There's a floss refactoring and a root canal refactoring. And the floss refactoring is basically you do some small changes in the code. Most often there are tools that are available there, and you just find small bugs, small ubiquitous problems. That's what the standard term is for that, and you fix those problems. So that's typically takes a couple of hours, a few minutes, couple of hours, at most a day of your time, and that's where it is. And then there is root canal refactorings, where it takes a lot of effort. It goes beyond tools, because there are, like, for such a big scale of refactorings, often all the steps are not supported by any refactoring tool. So you look at those and you try to, like, some parts of that is manual, and through a combination of automated tools and manual process over a period of few days, you make some major changes in that. So we had to give a catchy term name to the talk that came in. What we wanted to do was also look at the tools and also do the manual triaging of that, manual understanding, manual exploration, that way, over a course of time for a long period, and look into, like, what is the static analysis tools, how they're being used, and so on. So as part of this talk, building up this, we interviewed the maintainers about the best practices. We evaluated the results from some of the current practices, and we also analyzed the source code using some other solutions that are out there, whether there's some gap that is there and needs to be fixed by something else. So that's what the experience that I'll be sharing in this talk. So right now, Coverity Scanner is the one that is used in the CI/CD pipeline. It has been there for some time. What we did was we narrowed the scope, and we looked into all the bugs that were reported by Coverity between January 2024 and March 31, 2024, 3 months of time. And these reports were all public, so you can go to GitHub and you can search with Coverity issue tag, and you will be able to look at them. So it does, because the bugs are generated or reported automatically, it has the robot generated issue tag there, so it's very easy to find them. And but the bug reports, they typically do not have that much explanation. Oftentimes it says that it's just a heading that, okay, this is a bug, and then for more look into this, and then they are pointing to Coverity portal, which I did not have access to. So in some of the cases, when we looked into these bugs, we hoped that we would be able to look into more closely about, and give our judgment of whether this is a true positive or false positive or not. But in many of the cases, we were not able to do that. We were only looking at the GitHub commits and so on, and getting that. But in this particular aspect, or for these particular things, we more relied on how the community responded to the bugs. And the community response was actually pretty good. So there were total 77 bugs reported in those 90 days of time. There were 11 bugs that were duplicates. So we are talking about 66 bugs over a course of 3 months. That's actually pretty good for a bug detection tool. And of them, 35 unique bugs are already fixed. So that's a very good fix rate. About 50% of the bugs that have been reported have already been fixed. There's been about 25% of the cases where there are false positives. And these are identified, again, not by us, by the maintainers themselves, and so that's what we did, or what we looked into. There's 17 bugs that are still pending. These are the bugs where we were interested to see whether we can find more about that, and see, like, okay, are they pending because of some false positive or not? But again, because of the lack of information, we couldn't go much into that. But that's where we are. There's about 25% of the bugs that are being suspended, and they can go either way, this way or that way. But typically what happens is the higher priority bugs, they get prioritized, and therefore they get fixed faster. And the ones that are low priority, they typically, the ones that take longer time, there is a chance that they will probably be erring on the false positive side as well. And so most of the bugs that were identified were of medium severity, about 2/3 of them, but then there's about 20% of the cases where some high severity bugs were found. Many of the, majority of them have already been fixed. There's a few that have been labeled as high severity by Coverity, but then the community is not necessarily sure about that, but that's where what the lay of the land is. So here's a sample of a high severity bug that was reported in Coverity. So in this case, there is this comparison that Coverity flagged, and there is a macro that is being used, config num IRQs. There is a comparison done between table IDX being greater than config num IRQs before we are writing into the table IDX. So it's important that we do not write beyond the buffer bounds. And there is an check that is already established there. The question is whether this is a useful check or not. And so this is a bug that was flagged. So so we went into like what is the definition of this, and it is multiple defined under multiple different configurations, but it basically look into the different IRQs and different signal levels of interrupts, and then creating a sum of stuff based on that. However, there's this config num IRQs. There's also there's another corresponding check which is about the IRQ table size. So when we are writing into the table, it's better to look into the not the number of things that can be on the table, but also the table size, because in this case, because there's a start vector, there's a padding up front, so therefore the number of the table size is actually smaller. So if we were looking at just the aggregate, the sum based on the config num IRQs, it will take you, or it might take you beyond the buffer bounds. This is pretty clever. Actually, what Coverity did was it figured out the macro definitions. It did some length analysis, identified like, well, what is the length of the buffer and what could the access be, and so on, and reported the bug. And so the fix there was to move from the config num IRQs to the more reliable or actually the real metric that we should test against. So if it is greater than equal to the IRQ table size, it should be able to flag. So that was the fix that got added, and so on. So that's and not surprisingly related with buffers, whether you are writing, reading within or outside the buffer bounds. I mean, that's been where C people have been there forever. So and so that's one of the bugs that were identified and also fixed. Now there are some also, here's an example of a medium severity bug. This is pretty straightforward actually. Not very, it doesn't need a very clever tool to figure this out. But there's this function call in the red side, red line in line 2515. There's a function call that is there, and it is supposed to return some value and some error code as well, but no, there's no check on the error code. So it's just like creating a receiver and then assigning the error code and doing a check of the error code in that. Now in the second case, the fix, so I'm looking at it from a tool builder's hat, like can we build a tool? In the first case, the tool is, there's a tool that can easily be built. In that case, you just create a receiver, you just add a check, basically create a bypass, and that's that. What you're not doing there, however, is what happens if error is 0 in this case, or there's some error that has happened. What do you do there? Do you bail out? Do you crash and burn? Do you just print something and just move on? That's something that a tool builder cannot identify. So, and no way, it requires information that is domain specific, and specifically the maintainers need to come with that. So what it did in this case is, in the first one, it just did a bypass, but it did not say what is happening in the other side of the bypass. But it's probably okay, because in the bigger context of things, it's probably only doing something if error is if things are fine. But in this other case, there was some printout that's been added that probably logs and so on. So that's a sample of this. So now let's look at it in a different perspective. We also looked into what are the CVEs that were issued in Zephyr in all of its lifetime. So we looked into so there's a link underneath. This is also again publicly available. What are the CVEs that have been issued in this project for over a course of time? We see that in 2020, and perhaps because of COVID, we had more time, and so more bugs were or more CVEs were assigned. 2023, I don't know, inflation maybe, whatever, yes. But so what is important is in 2024 so far, in the first 3 months, only 2 CVEs have been assigned and so on. So because we're talking about buffer overflow, and buffer overflows are important, we looked into the most recent buffer overflow that was identified here. This is in a case where sprintf was used, as you see in the code underneath, and it was writing beyond the buffer bound. It's actually given a severity level of 7.3, which is pretty high. So we looked into that. This is the fix that was added to fix that particular problem, where we added some length check and then replaced the sprintf with memcopy and so on, and everything happened fine. So the fundamental thing about this is, and we have known this for a long time. Actually, the papers that we have written in 2010, 2011, 2012, back in the academia, we were all talking about this thing. There are functions that are fundamentally problematic, but we keep on using them. We keep on using star copy and star cat, even though we know that they're not good, and sprintf, even though we know that they're not good. And what's the challenge of just replacing them? And again, like, that goes back to my fundamental quest of why don't we have tools to, and in this case, the tool is not really hard to build even in many of the cases, because what we're doing is something in the static analysis parlance called length analysis, where the safe alternative of the functions that are there, they require an extra parameter, which is the length of the buffer. So the challenge for a tool is to identify the length of the buffer statically at a point of the program and use that information in the first place. So why can't we do that? So what we did was we just now did a GitHub search, identified like, okay, how many cases sprintf is used right now in Zephyr code? And so we identified that there are 68 cases right now. So we manually looked into all 68 of them. And so this is where I cannot do it just by myself. Our security research team, et cetera, helped us. We did divide and conquer on that. Most of the, I would say 67 of the 68 appear to be benign. They're okay to be used. One of them was a little bit interesting. So here's that one. So there's an sprintf which is printing out in this outstr buffer. It is printing a formatted string, and then there's some double values that are being used there. So, and that looked a little bit suspicious. And so this outstr, it has a size 64. So what we did here is we wanted to simulate a program, create a program that has similar standing. So this is basically the same or the similar program which has this same data structure that is being used, same functions that are being used there, but it is done in a small scope. Here, what we're doing is for values, we are providing maxint, as opposed to it can take any integer, but we are providing the maximum value that's available. Then this is printed to sprintf and so on. and now we are printing that particular thing. So we run this program. This looks to be benign, but actually there's a silent buffer overwrite that has happened here. So in this case, if we now create another buffer, so this format, because we're using maxin, the division, etc., it actually goes beyond the size of the buffer that's there. So we are just creating another buffer there, and we are adding another printf to see what that buffer is. Now we run that. Let's run that program, and now we see that even though we never did anything to overflow, it has the tail end of that previous one. Classic buffer overflow as there. Now you can tell, Munawar, why are you doing this? I mean, is this a 0 day? It's not. But this is coming in the samples code, so arguably, okay, it does not require that much scrutiny. Although in the recent wake of the XZ vulnerability, not everything is actually benign. Like, you might have to look into that. But what we did was we also looked into like whether this like out EV, like these values, how much of that can we control? And we were not 100% sure of whether that can be controlled or not. So we have brought this into attention, but that's something that I just wanted to show you. But fundamentally what this is coming back is to the question is, if we had we eliminated all the star copies and the sprintfs in this with a safe alternative of the function, all of these problems would be gone, because they are secure by design options for doing that. So, okay, so that's enough of Coverity. Now let's look into beyond Coverity. There's a code checker I mentioned that was introduced in release 3.5. We spoke with the maintainers. We understood that this is only used, not in the CI/CD pipeline, but not only used by the end users. And so it's basically a openly available tool that the maintainers are making available to the end user so that they can run the scans themselves. And so it does not find much. So 0 bugs were found saying that code checker was used in this. But last year, actually even before code checker was used, there was a couple of bugs that were reported. One about an uninitialized variable. It's actually not, not uninitialized variable, it's actually unnecessarily initialized variable. So there was a variable that was initialized, but it's not needed there. So it's not a big deal, but it's that kind of bugs that's identified by code checker. This one was a copy-paste bug though, and interestingly, Coverity did not find it, but they did, where they were looking into just copy-paste. So this, like when this was done, this first line was just copied into the second line, and so there should be like new checks in there. And so it's a classic copy-paste bug, but basically this tool was able to find it and in August of 2023 and not others. So what we also did was, now we looked into the new age tools like the sneaks and the semgrafs that we hear about, and then see like how much they work. So this is where we ran on sneak and semgraf. So sneak specifically identified a lot of stuff in the Python code and so on. That's another story. We can get into that. Specifically, we're interested in the C, C++ side. It identified about 40-something vulnerabilities. And then we manually triage. This is what we are good at. We, at our security team, we look at the bugs, we triage, we do the audit for and scale and so on. I've mentioned that. So out of the 41 bugs, there were 31 medium severities, 10 low severities bugs. So there was no high severity bug that were found. 27 of them were false positive. 14 of them, we are not sure whether they are true positives, but maybe worth a look, another look for the customers. Although we feel more strongly that those would also be false positives or not. So that's where the other tools that are finding in this space. And also we looked into semgraf. They have recently introduced a bug detection tool. They have identified 233 bugs in the C space. 3 of them were high severity, 60 medium, and 170 low severities. But there were only 2 potential true positive, and we also identified them as probably won't fix. But then 231 of them were false positive, so not worth anybody's time. So here's an example of a high severity bug that was identified as false positive. And this is what gives you an idea of like where the tools fail as well. So this was identified by semgrep under the rule local variable malloc free. So this expression points to a memory that has been freed. This can lead to a segmentation fault or memory consumption, memory corruption. So in line 403, it's flagging that, but this is just a free alternative, a library that is used to free stuff. And this is in the retarget lock close function. Where is it used? We look into the use of that. It is used in a test code, so okay, not that critical perhaps, but nevertheless, this is a library API, so it may be used in other cases. But here's a test code. But we see that there is a lock init that is happening. And so in the lock init, we look at that there's actual mallocs and there's these k-object allocs that are happening in line 365 and 367. So everything appears to be in good order. So we allocated some stuff, we used that, and we did that. But why is it identifying that as local? And we were wondering, like, okay, I mean, this looks pretty unnecessary. Like, why would a tool find this kind of stuff? And so after a lot of soul searching, we thought that it might be that because this lock T, it is used as a parameter, but because this is a non-pointer parameter, or it appears to be a non-pointer parameter, then it might think that, okay, this is a local thing, and then that might be throwing it off. But we really don't know why it is identifying this as a local symbol as opposed to something that has been passed as a parameter. And actually, it's not a non-pointer either. So if we look into the lock T, the define in that same space, we identified that it's a void star. So it's actually passing a parameter by reference. So there's no problem here. And then we understood that, and then we looked into what sort of, so tree-sitter is the grammar that is used by GitHub that is also used in semgrep's tool. And so tree-sitter does not have any understanding of the macros. So to a tool builder which is building on top of tree-sitter, they're looking at this macro, and this is just identified as an int or something that is not a pointer. And then it is probably looking at a release of a pointer and just like, oh, okay, what's happening there? But it's really on the foundations on which you are being built that is creating this problem. So anyway, so this is a journey. This basically talked about what we have found and what is in this space. Overall, we feel that Zephyr has a very good security posture. It is using Coverity, which is the best in class in the tool right now. And as far as that is concerned, it is identifying quite a lot of bugs. There's arguably about half of the bugs are false positive, but it's okay as long as the other 50% that were identified as true positive, including high severity, have been fixed already. But it does not find anything, as we have seen that there are occasional cases where a code checker was able to find something that was not found by the typical static analysis, by the static analysis in the CI/CD pipeline. Other tools we have seen are occasionally useful, but in general we have seen that they generate a lot of noise, so not being that useful. And and it comes back like that. There should be an active focus on coming up on tools that that can bring fixes or eliminate those classes of problems that we see recurringly from 1989. The first one, the first malware by Robert Tapp and Morris, the Morris worm. That was a buffer overflow. In 2024, we are still talking about buffer overflows. And from there to here, it's almost always like 80% of the cases are about uses of these unsafe functions. About 20% of the cases it's using like doing pointer arithmetic wrongly. So why can't we build tools there? So that's kind of where we expect that Open Refactory is going to be able to come and fill a gap, but at the same time, all the other tool builders should come in and do that. So thanks a lot for coming to this talk. I'd appreciate, if you have some questions, I'd be happy to answer. Yes?
I guess my big question is, if we know functions like sprint are unsafe, has there been any effort just to disallow them and decode entirely?
I don't know that. I'm not a maintainer, I'm just a third-party auditor at this point. My interest, I've explained that earlier. So I don't know that as a fact, but here's a survey that I did in 2008 when I was a PhD student at that point and looking into these functions and wondering why are people using them. We looked into GoScript at that time, in 2008. And there were about 700 something star copies and star cats. So at that point, I was also doing empirical studies. So I did a small empirical study with the maintainers of that, identifying like, why can't we do that? And it really comes back to time and legacy stuff that's being there, and we just don't have time to do that. And had a tool been there or now or any time, and if it comes to a check of like, okay, somebody's next 1 month where they don't have to do all the hard work, but a tool is going to find those fixes, somebody has to validate, run the test cases, and so on, that would have been great. We are just not there yet. But I don't know as a fact whether they're disallowing new users of sprintf, etc. in the code. And frankly, like we've identified that there were 68 cases of sprintf that are right now there. One of them looked a little bit suspicious, that's what I was playing on, but then 67 of them looked benign. So if a tool was just moving them from one to there just so that we don't have that problem in the first place, that's just good enough. Yes. Yes.
How do you deal with the fact that we don't write in C these days? We write in either Clang or GCC, which are not quite C languages. They have a bunch of extensions, they have a bunch of semantics. For instance, you can tag functions as malloc in free equivalence using function attribute. How do your tools deal with these more advanced languages beyond C?
It does if you provided metadata. Typically, like from my Coverity experience, what they did was they have a like a JSON data set where they kept track of, okay, these are mallocs, but these are what malloc likes. And then that can be something that is like you can configure it yourself, so you can add to that configuration, and then something that is malloc-like as identified by, let's say, Zephyr project, the tool can probably detect that. I mean, so.
Could you use the GCC and Clang attributes to automatically do that and accept that the language that you're evaluating is not C, but GCC or Clang?
That's a very good question. So if we were using, so depending on what parser you are building upon, in our case, for the tool that we are building, we actually have the parser entirely built for ourselves. So we understand whether this is a GCC extension or not. But in the case of Coverity, the parsing is done differently. I cannot say which one. But basically it is done by some other tool, and in that case, whether those information is available, I think that they should be available, but I mean, don't quote me on that. But I think in general, it's actually not that hard. Like there's the ANSYS that's there, and if you are writing or building up on a parser that is doing something else, then you can find that information. Yes.
How does the intelligent code repair play with like specific standards in an industry, let's say automotive or MISRA compatible?
So Coverity is very good with that. Coverity actually, when I was there, they purchased a company from Australia called Goanna, which actually did MISRA compliance, and all of that was integrated into Coverity. We also aspire to be there, but yeah. So right now, for example, Coverity is very good with that. So it does identify those. Yes.
Yeah, you mentioned that your tool has very low false positives. What's the key idea behind it? Because we know that the static analysis has some non-deterministic issues, right? Because of the branch,
Yes.
concurrency or whatever. So what's the
And this is exactly where we come in. So we do path analysis better than anybody else. That's what we did in 2016 when we built the C tool and these benchmarks were tested. So there is the Summit benchmark, which is created by NIST and DHS, which has tens of thousands of C code, C and C++ code that has, and examples of programs that have subtle variations where something is vulnerable versus something is not. And all of those, in all of those cases, so that's where we ran our tool in 2016. And when we built our Java, Python, and Go tools, we also tested against the industry benchmarks, and we have seen similar results. What we did is, or what we do, which is different from what Coverity did and does now, and all the rest of the industry. Now everything is going into AI and LLM, which is even more scary because coming soon, more false positive for you. That's what I can project, if it is done only by LLM. But what we do is we do path analysis, so we actually follow the path. You cannot, however, follow the entire path of the program. That's just computationally intractable. However, we do SAT solving. We identify like whether this path is taken, and corresponding to that, another path is being taken. And what the secret sauce of us is, we scale that to millions of lines of code. That's what we have identified, and that's why our results are much better than the others. But again, not there yet with C. Hopefully, sometime later in this year. It takes longer. So we will definitely not be the fastest, but it's not going to be so slow as in not worth. I mean, you don't watch paints dry. So you run it as a nightly build. If in the morning you get bugs, that's good for you. What happened in the last 10 hours, you don't care. But let's say another tool is going to run it in like 10 minutes, will probably take 2 hours. In the end, if they give you 20 false positive, we give you 2, that's what matters. So yeah, that's what the hypothesis is. But we are the slowest by far, yeah. Okay, thank you. Thanks a lot for your time. I hope I kept you awake. Thank you.
Check, 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 check.
Hello, can everybody hear me? Yes, okay. I'll be waiting. Let me know if when's a good time to start. Now? All right. Hello, everybody. My name is Luis Ubiera. I'm a lead firmware engineer at Croxel, and I'm here to present an open source contribution I recently made to the Zephyr project, which is, among some of the things, most relevantly, shell over Bluetooth LE. So let's go over some of the agenda today. We'll do a quick intro, then we go over some general aspects about Bluetooth low energy in a nutshell. Then we'll touch upon the basis upon which shell over Bluetooth it's built upon, which is either of a Bluetooth LE news. Then we touch on what Zephyr shell is. Essentially, we explain how to use shell over Bluetooth LE, and we do a live demo. We'll make sure to leave some time for asking questions. So I know not only you guys are here, but also this is live stream. If you want to ask some questions in the chat, we'll make sure to try to get to all of them if possible. So, quick intro about myself. I studied electrical engineering, even though ever since I graduated from college, I gravitated towards software. It's one of my passions, so that got me to be the lead firmware engineer at Croxel today. I've been around 7 years writing firmware and introducing bugs as well. I'm based in Melbourne, Florida, the Space Coast. Everybody always asks me, is that in Australia? It is not, it's in Florida. The good thing about the Space Coast, if you see that nice picture over there, is that we have rocket launches every other week. So SpaceX is always deploying satellites, and it's like part of the scenery of the area. It's pretty common to see them. I have passion for technology, electronics, and IoT. My first Zephyr contribution was in 2021. On my free time, when I'm not coding or doing engineering, I'm into fitness and sport. I recently started a blog that's called embeddedtales.blog, and I have a series about Zephyr called Zephyr, the Linux for MCUs. So make sure to stay tuned if you're interested in it. And nevertheless, this is my first time as an Embedded Open Source Summit speaker, so please bear with me. About Croxel. So what we do is primarily we are a team of engineers who develop firmware and design hardware for companies. So we do consulting and contracting. We have expertise in Zephyr, and we essentially kind of like typically assist clients and people who have needs that need to run on Zephyr. We offer different services from end-to-end product development capabilities. Also, we do rapid prototyping. And obviously, we're also open to team augmentation. So a typical use case where a team has a product or has a development they need to do, but they don't have the expertise to do that, we usually team up with them and work in collaboration to get it done. And finally, we are active in the Zephyr project community, so we provide contributions as part of what we do. So this is about the contribution. What's the status of this? So we published a PR around beginning of March, and it got a few iterations that ended up being a more generalized Bluetooth low energy transport for eWort. Initially, it was positioned as shell over Bluetooth LE, but we found out short along the way that there was a lot more value in making it more generalized so it runs over eWort and we can tap onto everything that eWort is already developed for in the code base of Zephyr. So that's why that was pivoted from that. The status it's that it's merged. I see a couple people here in the room who approved and reviewed the PR. Appreciate your comments and review on it. And finally, one of the things that I believe are interesting is that it faces a long-standing issue that was open since 2019 that wanted to get this done. So, okay, so let's go over Bluetooth LE in a nutshell. I just touch it on an overview, so I don't skip it, but I'm sure you guys might be familiar with this concept. So, Bluetooth in a nutshell, essentially when you have devices that want to talk to each other, they need to find themselves. They need to be aware of their presence. And the way Bluetooth LE does that is by the generic access profile, the gap profile, in which in general terms, obviously, there are some specific cases, but In general terms, the peripherals advertise packets to the, essentially kind of like broadcast and signal its surroundings that it's there, right? And you can put some information in those broadcast packets. And the central devices, such as like mobile phones, computer, and other things, generally more powerful, are scanning for these devices to obviously wanted to connect or interact with them, right? So the gap profile takes care of that. Peripheral devices are generally more low-power devices, such as wearables or embedded control devices that are more restricted. That's not there could be exceptions, but that's generally the case. And once you have them connected, you establish one typical way to do that is you go to the gap profile, in which establishes the scheme or the way that the two devices that are part of the connection can interact. So generally speaking, you have the peripheral, who is like the GATT server, and exposes a GATT database. Exposes like profile, implementing services and characteristics, which in general terms is just a endpoints through which you can interact in a specific manner, define what the profile does and what are the rules for it. And the central is the client. So essentially, it's like getting the information from the peripheral and exchanging and setting commands, receiving information, and whatnot. This picture here is an example, typical like a wearable that has like a heart rate monitor, and the client is a mobile phone that wants to consume that information for whatever purpose you might want to. So what happens, I'll go quickly back just to make one clarification. The Bluetooth spec has some standardized gap profiles, right? You have like heart rate, you got like battery monitoring service, among other things. Generally, people run into the problem of should I use standardized gap profiles or should I do custom ones? Because you can, right? Generally, the trend or the question you need to answer is if you want compatibility across different applications. The way to go with the standard GATT profiles is that you want different applications to understand what you want to do. Or if something fits your purpose, why not use it, right? In general terms, that is okay. But it could be that you don't find something that is already standardized. So that's when you run into custom GATT. And there are many ways in which you can implement this custom GATT services or custom GATT profile. One of the options is to go with a Bluetooth-centric GATT. So what does that mean? Essentially, you're building the profile in terms of the functionality of the device or the functionality that you want to expose. Here in the picture, we can see, for instance, like one characteristic per functionality. Let's say that you have one for button state, another one for LED control. That's what the LVS service from Nordic does, right? You expose the ability to understand what the digital input is and obviously command control the output of another one. Another example is what's there on the picture that you have. Let's say I want to have a motion detection service, right, or a profile, which consists of a single service, motion service, and you have like different characteristics. One for the motion state. Let's say that you have like an integer signaling whether you're moving or not. Another one, would you specify the motion location? So it may be a wearable, and you may wear it as a necklace, or you may have it as a wristband worn device, right? You can also have like a motion count. So you have to keep track of the number of events that have like transition between moving or staying idle. And you can obviously control it. Let's say you want to enable, you want to disable, or you want it in a specific mode. That's also possible. This is typically the way that standard Bluetooth LE services are structured on, exposing the functionality so that applications can understand what's happening. The other approach would be to keep it generic as possible. So in that sense, essentially, you're just exposing the GATT service and the characteristics in such a way that you are just putting the endpoints or the ports, and then essentially the meaning of that information will be determined by the content of that payload. In this case, that is generic. There is no insight of what is going on with the application will be the payload, as I've already mentioned. And basically, you generally have to come up with a schema to parse and encode those commands. The benefit of this, even though it's not the way that Bluetooth LE generally works, is that you can have it as one of the main of the different transport of a specific application or services you're providing. Let's say you have it a transport, you have a functionality that goes over UART, and you have another one that goes over, I don't know, an IP protocol, and then you want BLE as well for that. So that would be one option in which Bluetooth is one of the backends of the service you're trying to provide. Sounds a lot like serial, where you, for instance, you may have like a transmission characteristic and you may have like a reception characteristic, and essentially you just one for transferring data and the other for receiving. And that's what brings us to UART over Bluetooth LE, NUS. I'll talk about what NUS is. Essentially, it's a custom service. NUS stands for Nordic UART Service. That was a company who developed and came up with this service. And essentially, as I mentioned, it does exactly what I just described before, where you have like a transmission characteristic where you can send data, and you have a reception characteristic from which you can receive data as well. It's similar to what the serial port profile does in Bluetooth Classic, and it's, I need to mention that this is not standardized. So this is a custom service. I understand there were efforts to standardize it, but didn't get through. Even though that's the case, it is widely used in Bluetooth LE applications. So if in the past you have tried to do something about a serial port over Bluetooth LE, chances are you've run into this. So the way to enable it on Zephyr is basically, among different things, one of the important aspects in Zephyr is that we have it abstracted behind the UART driver. So not only you can interact it as a Bluetooth LE API with a service, but you can treat it as an UART device. And what that allows you to do, as you guys can see in the picture, is that you can declare it and I would say instantiate it on the device tree. So it's like I have a serial device with the compatible property of Zephyr, NUS, UART, as you can see there in the tree. And the benefit for that is not only you can have multiple instances, as in a device tree may have, you have multiple UART ports or UART devices you can pipe data through, but also you can redirect subsystems that should be compatible with UART to be routed through the Bluetooth LE as well. So here is like one simple demo we can do. Blinky with the console routed over Bluetooth LE. I'm going to try to do this live. Hope it goes all right. And the command for doing that essentially is just we define board, a target, and we provide a snippet. Essentially, a snippet makes it easy for linking what needs to happen on the device tree alongside with kernel configurations or project configurations. And it's available in the tree there. So we'll go ahead and build this. Samples, basic Blinky, we'll erase it, and we'll use a Python application, essentially any client that you might come up with that's compatible with it, to see how it works. Hopefully this will turn out all right. I hope you guys, can you see my screen? Okay. Let me clear this. I will. So we provide the snippet, and then we say what application we want to build for. Let's see. I just tried this a few minutes ago, but hopefully, okay. Seems to go all right. I have here a development kit wired up. Just one FYI, I see some pictures being taken of the slides. They're available on the schedule, so you could continue to take them, but just they will be available for you guys. So I'm going to flash it right now. This failed. Let me try again. Oh, that's really nice. Let me see what's going on. So this is obviously the onboard J-Link that's in here. Obviously, it's an emulator. If you have like a J-Link dedicated for it, this shouldn't happen, but in any case, we got it through. So right now, what I'm going to do is I'll open a new tab, and let's go with the client. Essentially, I have here one scripts, Bluetooth CLI. This is just a Python application, and let's see. As you can see, this is not connected over UART, even though we have here the USB, and it has like, it is essentially kind of this scanning for the devices. The board is broadcasting with a new service. The computer is finding it, it's connecting it, it's subscribing to the characteristic to receive data, and you're getting that. So you have like console over Bluetooth LE. That's one of the benefits for this. Okay. Let's continue. So that was good. let's talk about the Zephyr shell then, which is generally not going to this part of the presentation. We make a lot of emphasis on how useful and important Zephyr, the shell subsystem is for Zephyr, and there are many reasons for that. One of them is that it has extensive support in the tree. So essentially, the shell, as you guys may know, it's like a command line interface that in which you can define and implement commands in a essentially kind of like command response basis to execute some actions or query some information. Just going over a little bit of the generalities for this is you can define custom commands and use them in a pretty simple manner on the firmware side, and you can use the commands that are already there in the tree, which is a lot of them. We'll go over those. The way to define a command if you want to implement a shell command for your application, essentially, you have two general options. There are like different permutations, and you can have like some complications, but keeping it simple, you have the ability to register a shell command in which you define the syntax. Essentially, what is the command? What do you want to execute, right? Then you have the ability to provide subcommands, so basically not only the command, but some variations of that. You have a help string just to provide guidance on how should the command be used, or what are the arguments, what are the expectations that the command expects so the user can use it in an intuitive manner. And finally, a command handler. So this is the function that gets executed when the command is detected to be issued, right? If additionally, this is too limited for you, you want to provide arguments to that shell command, you can do so by using this other macro. Well, you have the shell command argument. Additionally to whatever everything I said before, you have two additional arguments. One of the mandatory arguments, the number of arguments that are supposed to be mandatory, and the other one for optional arguments. The function handler, this is pretty general, but in a basic and fundamental view, with the way you would use or implement a function with shell would be just to receive the argument count and argument value. So this will be provided as strings, as an array of strings, and essentially you just validate the inputs, make sure that it matches your expectations. You execute the function that it's meant to be implemented or executed, and then you just return a result. Additionally, you may provide like some context or information as you're executing this function in a print K fashion using the shell print API. Essentially, you can say if there was an error, what was the error, so you can provide some description of what happened if something went wrong or if it didn't, or if you needed to provide a feedback, a result, or a value, that's how you would do it. So going right now, like tying all the loose ends, I already explained what Bluetooth LE was. I explained how to map it like a eWord over Bluetooth LE and how to taking it to advantage for the different subsystems. But generally, in true, like the Zephyr shell has different backends, right? The first one would be like the serial, in which you can use it for eWord, USB, or BLE. You could have RTT, which is right over JLink, if you wanted to. You can have RP message for interprocessor communication, right? So that can be implemented. MQTT Telnet and MCU Manager. So we've mentioned that the commands and shell commands in Zephyr have extensive support, and that is not an overstatement. There, literally, all over the pieces of code, you have shell commands for the different drivers and subsystems, and this is not an exhaustive list of them. As an example, you can use shell commands to control the I2C devices. You can control ADC, GPIO for reading and setting digital input and output, PWM, CAN bus, flash, sensors, and LoRa. One typical example, for instance, of how this would be useful would be when you have like a board and you want to validate some of the components, but you don't really have code for it. It's just a one-off basis type validation, and you can like issue I2C commands manually to see if the devices are there, or you just like perform an I2C scan, control GPIO pin, so you just set an output to enable a regulator or some other thing, right? You may be interested in interacting with, or just literally reading some sectors of the flash. Right, those typical uses. For subsystems, you have more commands, more shell commands like Bluetooth, audio networking, anything you might come up with or you might be thinking in terms of like Wi-Fi commands, Ethernet, or IP-based protocols, you probably have shell commands for that. MCU boot, logging, storage file systems, and LLEXT as well. So, ton of commands, probably miss a couple of them, but just a general picture, shell is tightly coupled or tightly in one of the core foundations of what Zephyr is offering, so make sure you can use it if you want to. Finally, we now tie everything together where, okay, so I'm interested, I want to try shell over Bluetooth LE, how do I do this, right? So it's generally a two-step configuration, where first of all, you make sure you have the key configs to enable the relevant modules that you want to interact with. And that's like kind of like serial, you need to enable serial, you enable the shell, and you enable Bluetooth plus news. Additionally, we have some optional configurations which may be useful for you. The first one is about auto-enabling Bluetooth. So if you're running an application that does not really handle Bluetooth on its own, and you just want to try it, let's say like the Blinky sample I just showed doesn't really enable Bluetooth, right? So by enabling this configuration, it'll auto start, like a systemd type thing. And finally, some throughput optimizations, but just a disclaimer, it's not a one-size-fits-all type thing. Your application may have different needs, and it's important that you keep that in mind. And the other part is the device tree. The device tree, just as I mentioned before, you instantiate the node, the device tree node, to be compatible with Zephyr News UART. You additionally, so internally, that implementation has like RX and TX FIFO sizes, so you may have different endpoints with different constraints. Maybe this one doesn't need that many bytes of FIFO, and you can optimize that for your application. That's perfectly feasible. And you essentially just write the chosen property for Zephyr shell UART. I want to redirect that to BT News shell UART, which is the node label in the instantiated node in this case. So let's go with a live demo. I think you guys all been waiting all along for this. Let's see, does it even work? For this demo, I'm going to be using one of our Croxel prototyping boards. This is like a BLE node that we have open sourced. Essentially, it's a Nordic. It's got a Nordic chipset inside of it. Is really like an Azure Alert BL654. And it's got a ton of sensors, essentially. You have like an accelerometer, you have like a ambient light and RGB color sensor, temperature, pressure, humidity. So it was one of the sensors that we developed when we were playing and wanted to prototype for low power applications. The source for the design files for this, it's available on this link on croxel.com/BLE. Just not to distract the meeting, but just like, hey, this is the schematic for the peripherals. Everything is mostly tied over I2C. You have a bunch of I2C peripherals that you can talk to, including everything I just mentioned. I think I didn't miss anything. But it has, for instance, a Hall effect switch, so you can use a magnet with it to detect the presence of it or not, and among other things. This is on the slides, and it's on the website as well. So let's go with the demo that we promised. Let me go over here. So what I'm going to do is I'm going to, hopefully you have the command saved here. If not, I have to type it myself. OK, so here we are building for, let me clear the screen. And let me show the command again. OK, so what this command does is builds an application for the CX1825, that's the board, and it's got an RF52840. And we are targeting the sample subsys shell module. That's the shell sample. On top of that, we are providing the kconfig overlays, the project configuration overlays, and the DTS overlays. These are overlays -bt.conf and bt.overlay. And we're enabling a bunch of subsystems so that we can play with them here on the demo. If you're not familiar with this syntax, essentially after the sample, you can provide some flags so that you can, on a one-off basis, can include some additional components for you to play with. But that's not permanent. As soon as you erase the build directory, it'll get cleared up. OK, obviously we needed to clear this. Let me see. So as I'm doing that, I'll be wiring the board here. Okay, so it built successfully. Now I'm going to connect it over SWD. Let's flash erase. Let's see. Does this work? No, hold on. Bear with me for a sec, please. There you go. Okay, so we have the board here. Let me see, let me clear it here as well. There you go. So we have here the shell interface. I'm pressing tab here, as you can see. It's working as if we had it wired over USB or UART. And we can do many interesting things. Let me see what we can do that could draw your attention. First use case, for instance, if you want to do it like a board bring up or something, you can do an I2C scan. We have a bunch of devices in the bus. So as you can see here, you can see 1, 2, 3, 4 devices on the I2C bus. That would be a nice way to say, hey, are these properly powered? Can I actually talk to them? Right? That's one of the things. Additionally, we can issue the LED command. So it's got the ability to set on an LED. So let me see if this works. Okay, I'm not sure if it's visible, but there's like a red LED on. I can turn it off. As simple as that. If you have support for your specific LED, meaning if you have like a charge pump that talks over I2C and there's driver support for it and you enable it, you can use just this shell command to talk to it. And let's play with the sensors. Additionally, for instance, let's say sensor. So before I go into that, you can use this very useful command. So this concept of devices in Zephyr is everything that's kind of like a driver that has a purpose. So this includes, as you guys can see, LEDs, the I2C device, the bus, among other things like this, the individual sensors. We have the APS 9960, the light sensor. We have the LIS 3DHS, the accelerometer, and among other things. So you can have like an idea of whether that device was initialized properly or not. And the way to know that is if it says ready, it was successfully initialized. Otherwise, it would say disabled. And this time, I don't think there's anything that's disabled, but that'll be one interesting way to see, hey, was this initialized properly? Finally, for instance, let's get some data. So if we wanted to say, for instance, we want to say orientation. I'm going to copy paste this, hopefully. Well, it turns out I don't need to. So here, for instance, the accelerometer positive axis here in this case is Z. So if I issue this command, I'm going to see that, obviously, the units for this is meters per squared seconds. So right side up, 9.8-ish meters per square second. As you guys can see, that's the case. I'm moving it, so obviously it may be changing. I'm going to flip it, so facing down. We should see minus that, right? We can see that's the case. Same thing with this. Let me see what's the axis. So this is X positive, this direction. That's the case. I flip it, and we see it. So it appears to be working. Let's see another sensor that we may find interesting. Let's see the light sensor. So you have like first you have proximity light, ambient light, and RGB components of it. So in this case, this is subject to the light of the room. I'm going to cover it right now. Hopefully I can do it one-handed. And as you can see, the values drop down. So it appears to be working. Additionally, the proximity seems to be saturated, I believe, 255. That will tell me that, hey, it's in close proximity to this. Let me see what other case. Let me see. LPS 22, I think that gives you ambient temperature and pressure. So it's around 24 C. I believe at least the board believes that's the case, and the pressure seems sane, kilopascals. Let me see what other things we can do. I believe, additionally to this, you can not only with shell, but also you can route other subsystems. In this case, we have both shell and the logging subsystem pipe through this, as you guys could see in the beginning. So you could do a log test, for instance. Start. Oh, demo. So right now, you're just like generating logs, and they're being transferred Bluetooth LE, and the computer is picking them up. Let me see if I can. Let me see if I'm able to stop it. Log test. Stop. Did it not stop? Okay, well, there you go. It took a little bit of time. This is using deferred logging, so it is not blocking the execution of your application. So it's just like putting them on the buffer in a low priority thread, and when it ever gets time, it's just putting them out. So this will not severely compromise your application. Obviously, there is some overhead that should be considered. Okay, so I guess coming back to this, I believe that leaves us around 10 minutes for questions. Let me turn this off. By the way, I have this board that I have a few for a giveaway, so if you're interested, just reach out and probably have some for you. Thank you. Any questions? Yes? Does this work, perhaps? Let's see. Here you are. Right. Okay. By the way, I don't know if the microphone's working, but I did get your question. So the throughput considerations, what's the implication for sort of Bluetooth? Certainly, and that's something that probably I should have mentioned, is that when you're going with shell Bluetooth, you're not really caring about throughput performance. This is improved flexibility, because literally well, in this case for shell, right? Not for news in general. For shell, you're just like putting characters out, like ASCII characters, UTF characters, and obviously that may not be the best for your application. You may want to go a different route if you wanted to optimize for it. So I haven't characterized it, but that's generally not what in principle this is for. This is in pro of small commands, a lot of flexibility. So a typical use case would be, what if I wanted to implement a CLI, or I have a set of commands for provisioning the board, your device, exercising some of the sensors, and you don't want to have to change the GAD database every time you want to add new functionality on it, because that's something that's it's a moving target. You are coming up with new requirements. You want to do new things. So instead of just restructuring what the GAD database is supposed to be, you just add a new command, and it's going to be recognizable. And obviously, just making it on top of shell makes it really easy so that you don't have to parse the new command. You just put the function handler you specified in that standardized manner. What are the arguments and what are your expectations, and that's the way you work it. And at least that's how Croxel has used it in the past. But that's a good question. Carlos.
Thanks. So I was wondering whether you've tested multiple of or several of the clients that are available out there, whether you have recommendations, which clients to use.
So I don't have a particular recommendation, I would say. I mean, if you just like Google News Client, you'll find a ton of them, particularly the one that this Bluetooth CLI has come up with. It uses, I don't recall it specifically, but it generally, there's like a ton of support for that. So unfortunately, I don't have a particular recommendation, but I can tell you that there's a ton of them. I believe Nordic has like some open source implementations that you can leverage for them. Obviously, they developed it, they maintain it. But yeah, that's the case. I'm sure you won't have a hard time finding support or for what you're trying to do.
And the follow-up, thanks. Yeah. And the follow-up, the one you were using was using then the built-in Bluetooth from your MacBook, or did you have another board?
Yes, okay. It's the built-in from the MacBook. I would assume, depending on the limitations, it may or may not work. In this case, I didn't need an external Bluetooth controller or anything, but that could
Right.
perfectly be the case as well, generally, yeah.
Okay, thank you very much.
Yeah. On top of that, I can say at least I've used it on Linux, Mac OS, and I don't think I've tried it on Linux, on Windows. I guess if you, I don't know, that's the only thing I haven't tried.
Any other questions? Oops. Who had their hand up? Okay, thank
He
you.
had his hand up.
Yeah, just curious, have you tested multiple instances of this? It just occurred to me when you were doing the logging test that
Right.
you could potentially have logging going over a different
Yes,
connection.
yes, I've tried it, even though I haven't stress tested it. Obviously, in the end, even though you have different endpoints, right, it's the same protocol. You're still exchanging packets every so often in the connection interval and whatnot, so there are definitely limitations on that. One typical sample that I did, essentially, I had like the console routed over one end and the shell on the other one. So obviously, the throughput required for the shell is not that much if you're not like doing extensive commands exchanged automatically. I generally just like type help or something, and then on the other end, the console was just outputting message. So I have tried it. It does work, although I don't know what the throughput limitations for that are.
With the client you're using, how do you select which one to connect to?
So in this case, it's this very limited implementation. It's open source, so you can check it out and improve it a lot better. But essentially, the way you would tie those things is by the attribute handles. So even though they're the same service, you may tie them by, hey, this is your application. You say the first instance of this service, it's meant for this purpose, and the second one would be for that. And that's how you would tie those things together.
Okay, thanks.
Yeah, no worries.
Is there a Linux implementation of News as well, of the server side? Or if not, have you considered contributing
On
that
the
to
server
Linux?
side, well, this is on Zephyr. No, this was meant for particularly my needs and what my applications were needing, which was a flexible CLI over Bluetooth. I said, hey, shell is already there, and we use it for USB. Why not using it over BLE as well? I don't think if there are implementations would be a nice follow-up on that. Yeah, thanks for your question. Unfortunately, I don't have an answer for it. One last remark. I don't know, do we have any comments or questions on?
No, we're having troubles with the technical game that's
Okay.
through. So if there's anyone that wants to ask questions, please use the ZDS-24 in Discord, and I'll just go check that right now. But I think we're pretty much out. So
Right.
yeah, look in Discord afterwards, and maybe if there's some questions tagged
sounds
to you,
good. Yeah.
then we can answer them there.
Yeah, tag
Okay.
me at Ubieda, and probably I'll be able to answer your question. One thing I didn't mention in the presentation, and since you guys haven't asked, is like, what are the security implications of this, right? You have shell over Bluetooth LE, and it's accessible everywhere. Anybody can pull up a phone and interact with it, right? Big disclaimer: you should use, you should not use this way, just like in your application, and then go to production with it. You definitely should use authentication and any validations. There are ways that you can have like dynamic shell commands, so you could like hide them behind a specific state, or just like require authentication. Moreover, you can use like the BLE encryption and authentication procedures that are there already supported. So please do your due diligence to understand what are your implications of just enabling this. Just please don't go ahead and enable this and put your products out in the field, and it's great to implement it because people will easily interact with it. It's pretty intuitive. Anybody can just type a tab and it'll come up with a few characters that are human readable. So just done with that comment.
Well, if there's no more questions, we'll say thank you very much.
Thanks everyone for your time. Oh. Thanks a lot, Katie. Let me turn this off.
want to use it for question and answer.
Test 1, 2.
Hello, everyone. So we still have 1 more minute, so let's wait for some people to arrive. Okay. Hello, my name is Daniel. I work at NXP Semiconductors. I'm part of the Linux BSD team. So my experience is mainly with the Linux kernel. And for this presentation, I will tell you my thoughts and my perspective when working with Zephyr kernel, with Zephyr OS, on adding support for a new board. So the presentation is structured like this. We will discuss about some goals that we want to achieve during this presentation and some things to get out of this room. Then we'll have a short introduction into how Zephyr development environment works, which is the Zephyr release cycle, and how to get started with Zephyr development, like getting the toolchain. Then you will have a short look on the new hardware module that was recently introduced, which is named Hardware Module version 2. Yeah. And then I'll share my experience coming from the Linux kernel community and my experience with this new community, with Zephyr community. So let's get started. This presentation comes as a guidance for newcomers. And what are the initial steps you need to take in order to get started with Zephyr? Then provide a short insight into the process of adding a new board. From my perspective, this version 2 model is very straightforward on what you actually need to do to have your basic support in. Then about the community collaboration, we'll start with how you do your first contribution and what are the iterations that you need to do so that you can finally celebrate your patch acceptance. So let's get started with the Zephyr release cycle. This is pretty similar with what Linux kernel has, with some differences. First difference is, and it's quite a shock coming from Linux kernel, it's that you're no longer sending patches over email and using GitHub. Right. The release phase is, the release takes 2 phases. One is the development phase where actually code gets merged, work is done, there are a lot of talks there around your pull request. This takes up to 3 months, and then at some point, development stops and people are starting to test the code really well. Of course, there will be bugs, and there will be a period of 1 month when community needs to fix the bugs. This is in a series of 3 release candidates. And after this month passes, the stable release is out. Now, there are 2 parts of the maintenance things. For the periodic releases, we send updates, bug fixes, and security fixes for at least 2 cycles. And for the long-term support, every 2 years, we mark a release as supported for long-term, and we support that release for 2.5 years. Now, here is a short graph of how things happen. So, for example, after 3.5 is out, the merge windows opens for the next release. All the development happens on the main branch. Then there is this period for development, which takes 3 months, and then we get the first release candidate. At this point, after 3 months, we branch out with a new release, which will be 3.6, and we add a tag to that release so that people can build a binary and put that to test. After 3 iterations like this, the stable is out, and we restart the cycle with a new release. There is no next branch like the Linux kernel has. So in the stabilization phase, most likely you will want to stop the development for new feature and concentrate on bug fixes. Now, what you need to do in order to have a simple application compiled, you will first need a toolchain. Fortunately, Zephyr SDK supports most of the architectures and most of the operating system, important operating systems like Linux, Mac, and Windows. And you will have hosts for x86 and ARM64. And targets are listed on the right and have the important architecture already supported. So most likely when you start adding support for a new board, your toolchain will already be there. Now there is an exception, and that's the Extensa architecture, which I will base my example on. Because when integrating a CPU from Extensa, part of the CPU configuration will come via the toolchain. So for each integration, you will need to create a new toolchain. And you see here, we support lots of integration of Extensa, mostly as a result of the Sound Open Firmware application that runs on Extensa DSPs. And you see here the vendors from MediaTek, Intel, and i.MX from NXP. But that's not really an issue. Adding support for a toolchain, it's quite easy. The important aspect here is that it takes some time. So if you look at the date of the commit here on August 21st, and we'll look at the date when this commit actually gets merged, you'll see that 1 month has passed, right? So you need to allocate on your project at least 1 month for the toolchain to get merged. The actual support for the toolchain, we use the cross tool, toolchain generator, and you need to create a config file where you add some definitions there for example, the name of the toolchains and some flags. And then another important thing is that you want to add this toolchain in the CI so that the CI will generate the binaries for you. Once everything is there, hopefully your toolchain gets merged. And we calculated that if you look at the date of this release is on 1 month later, right? And once you have this toolchain, you can start working on your actual board support. Now let's have a look at the board support. And as an example for the board support, we will have a look at the i.MX M+ AVK, which comes with a lot of cores that you want to work on. And actually, all the cores that are here are supported with Zephyr. You build a binary for each of the cores, and of course, each one is dedicated to a specific application. And we have these A53, M7, and the Hi-Fi 4 audio DSP here. Now let's look at the building blocks. As you can see here, we have the main CPU with the Cortex. We have the secondary cores with the M7 and the DSP. And the rest are just IPs that are on the SoC, like the audio interfaces, I don't know, PDM, DMAs, and everything one needs to have an actual non-trivial application there, and some peripherals. And we simplify this furthermore by showing the evaluation kit that has a SOC and the peripherals. And the basic goal of the presentation is to create and see the steps in order to create a minimal application that runs on the Hi-Fi 4 DSP. And the minimal application that everyone, I think, might know is the Hello World sample. That actually prints Hello World on the serial console. And in order to get this enabled, you need to have the CPU support, the UART driver, the pin control, the muxing of the pins, and some clocks, right? And let's see. With this hardware in mind, let's see what we can do. First, some things about this hardware model V2. We added support for all these CPUs before hardware model V2, and that felt very unnatural because everything was scattered around Zephyr directory hierarchy. And with this version 2, everything falls in place very natural. And this is one of the reasons it was introduced to support asymmetric multiprocessor, like SoC having different types of cores. Now, the hardware is modeled inside Zephyr into layers. And when trying to add support for a board, you look at each layer and see if the support is already there, or if not, then there is work for you to implement it. The layers, we will see later a picture with all the layers, but the main layers are the architecture type, the CPU, the SoC family we'll see later, and the board part. This model version 2 is in the current release, current working release, which is 3.7. And from my experience, I'm not sure if that's true or not, adding support for a board is like 80% writing configuration files and 20% actual C code, right? Support for specific stuff there. At first, it might be very confusing, and you might get a lot of trouble understanding what kconfig file do you want to add, where to add the DTS and stuff like that. But as usual, and as always in open source development, you just try to find a board that's similar with yours and follow that example. And another trick that I always follow is I look inside the history, inside Git history, and see the steps and how the commits were arranged in order to introduce the board. That's a very good example. If you find a board that does this, then you are mostly saved, right? Now, before going to details, we have some terminology that will be used across this presentation. And actually, what is a board? We call a board the target system that can actually load and execute the application image. Now, the board target is the full string used to compile an image for a particular hardware. You will see that for a board, we can have multiple board targets. Now, the board name is just a tiny part that we identify in a human readable way, the board. And the board qualifiers are appended, are some additional tokens that are appended to the board name to create a board target. And here we have an example with West build. You can see how the format of the target looks like. It has a board name, starts with a board name, then with a board revision. Usually you don't have the board revision. That's mostly optional. And then you have the board qualifier parts that selects you the SoC, the CPU cluster, and sometimes you can have multiple variants for clusters, right? Like it's SMP or not SMP. So this is the short description of some terminology that we'll be using from now on. Now, let's go to this picture, which, by the way, the documentation from Zephyr is very, very good. Very good. This is a picture that I've taken from the documentation folder with some modification because I think it needs some of the adaptation to explain better the version 2 of the hardware. So as we said, Zephyr models the hardware as layers which build one on top of the other. And we start with the architecture and CPUs types, and then we get into a part that's related to SoC. And we split this into a SoC family. A SoC family is usually a group of related chips from a vendor. And then a particular instance of a SoC family, it's called a series. And then inside that instance, we can have actual SoCs, right? This is sometimes, and at first, can be confusing when you add support for a new board because you need to understand your hardware and the family of the hardware really well in order to get this correctly. And then on top of that comes the board implementation where you actually select the SoC and additional devices that you want to enable. Now let's have this instance with the NXP family. Sometimes naming can be confusing, but we shouldn't get lost into these details. After some iteration, you will learn by heart this. As for the architecture, on our hardware that we want to implement, the 8MPFVK, you see we have 3 types of architecture here: ARM64, ARM, and Extensa LX6. Then as for the CPU types, we have A53, M7, and Hi-Fi 4 DSP. Luckily, when you add support for a new board, all of these 2 layers are already there. Support for this are already there for you. Now it comes the part that you need to actually do is to identify the family, series, and SoC. And this everything comes into Zephyr hierarchy in the SoC vendor, SoC family directory. And then on top of that, you add the board implementation, which usually comes in board, vendor, board name. Now this board name should be unique because they are directory inside the vendor directory. There is a West boards option that lists all the existing boards in Zephyr, and you can get some inspiration from there, but you shouldn't add a name that's already there. Now, let's actually start doing the implementation, and the first thing we want to add is the, inside the SoC vendor, we need to look at the SOC YAML file. That basically describes how your SOC looks like in the Zephyr model. And we have the family, it's for NXP is named NXP i.MX. The series is 8M. And the SOC name is this name that doesn't make any sense at first, but you need to look in the data sheet and take this SoC name from there. And then we define the clusters. A clusters can contain CPUs of the same type. And we have here multiple clusters for different types of the CPU, and we have ADSP, A53, and M7. Now, we'll have a look at the family. As I said, the family is a group of related chips from a vendor that shares some similarities, like features, architecture, design principles. The implementation files can be found in SoC vendor SOC family. And here we have some families from NXP, like the i.MX, RT, and S32. And also look at our neighbors, Intel and Nordic. They have some families there. Now we go and look at the series. So inside the family, we can have multiple related SoCs. And the families here for an IMX can be 8M, 8ULP, the new 9 family, right? And you can see here we have a bunch of CMake lists, kconfig files. We will discuss about important ones later. But most of these kconfig just help you to reach to the next level. Basically, they are including all the kconfigs from the subdirectories that are below them. It's not nothing complex here with these kconfigs. Now, let's have short navigation through these kconfigs. As I said, we start with this kconfig SoC. And what basically this entire hierarchy of kconfig is allow you to select each layer. So we start with the ADSP layer at line 12, which basically selects the SoC that we are using. And then if we go at line 8, we are selecting the series. And so on, going to the first line, we are selecting the family. The only thing missing here is how do we actually select the ADSP one at line 12. So we are now in the SOC area, and that config is selected from the board part. Right? And we'll see later actually how this is selected. Now, what is a board? We've already discussed a little bit about it. A board is the target hardware we want to build an application for. And the important thing here and the nicer thing is that this hardware model actually decouples the hardware from the application that's running on it. And the abstractization is done by the board. The hardware is implemented until board, and then applications are built on top of the board and can enhance and add overlays on top of the board. Now, the boards, all the boards are in the Zephyr boards vendor name. That's another enhancement brought by the version 2 model. And this directory contains some important files that we start with, and some of the other files which are optional. The important files are the board YAML, the kconfig with the board name, and the actual device tree for the current target that we are building. If we look on the right side, we see that each target, like A53, ADSP, and M7, has their own YAML file, DTS file, because it's actually different hardware, even if in the same board, and a file named default config, which helps you select some default options, config options. Now let's see what does the board YAML contains. This basically describes the metadata of the board. And we have the board name, it's most important, vendor sometimes, and the SOC. The SOCs are described here. So now you see how we link the board with the actual SOC that it contains by this file. And an important note is that the CPUs are not described here. The clusters are not described here because the clusters are contained by the actual SOC, and that's the way we bring in the exact clusters. Another important thing is that you may have multiple boards defined in the same board directory. Let's not get into that detail because now we are in the level we want to implement something that's very simple and very easy for us. One of the things that's also borrowed from the Linux kernel is the description of the hardware, which is done via the device tree. One surprise for me was that the device tree are not actually working as in the Linux kernel, where the device trees and the hardware description is parsed at boot time. And the hardware is actually discovered at boot time. With Zephyr, the hardware and the device trees are parsed at compile time. And everything is already there when you have the image. Now, our goal was to add support for a minimal SoC that can run the hello world. So what we actually need is to add the description for the CPUs, and we have here the CPUs from Tensilica. And then we need the basically the serial console, the UART, the UART, and things that make the UART work, like the pin control and the clocks that are described on the right side. Yeah, and once you have this device tree, this helps compiles and select you at compile time the hardware that you actually have. And now this is the final piece of the puzzle for the board, is how we actually get everything started. How do you actually, what's the entry point that selects everything on the compilation side? And that's the target name that's passed to the to west command. And you can see here, we have the target name is i.mx-mp-avk, that's the board name. And then are the qualifiers, the SOCs and the CPU cluster. And of course, at the end, it's the hello world part. Now, once you pass this name to the west build, there are some magic happening inside the CMake files. This magic, what actually does, it sets some variables with the names that it can infer from the input of west command. So here from the input of the west command, it can create the variable which is named on line 3 in the image below, which is named i.mx8 ML8 ADSP. And if you look at the parameter of west, of -b parameter, it's exactly the name of this variable. And this variable will select the ADSP1. And if we go back to the SOC directory, we see that this actual ADSP config was the one that started everything, right? And once we do this, we have the actual firmware image that we can load. And we can do the same for the other CPU clusters, like for the M7 and for the ADSP. Now, usually, what we also need here is some tools that help you load the image and boot code or something like that. But the nicer thing that we've encountered with this Hi-Fi 4 is that we load the Linux, the image from the Linux kernel side. So we don't have to deal with this on the Zephyr side. We just, Linux puts the image somewhere in a memory and just press start button. And at that point, the Hi-Fi 4 starts running and initializes devices and calls into the main function of your application, which in our case is the hello world one, which prints hello world. Now, that's the basic steps that you need to do for a simple implementation. Of course, for more complex stuff, you will need to add more drivers and more drivers for your devices that can do the work that you need to do. Now, let's see, we have the code. Let's see how can we get it upstream. First thing, and I was very surprised because when I started working, I just jumped into the code and jumped into the process. I didn't read the documentation. But my advice is start reading the documentation because for Zephyr is actually pretty good. And there are guidelines for basically everything you need to know. Sometimes there might be some boring reading because there are a lot of things to read. But you can find the answer to almost all your questions. And also, for the community, there is a Discord channel where actually everything you can think of has a sub-channel. And it's harder to find the sub-channel than to actually find the answer for your question. So there are guidelines for the contributions, for coding, for another trick that you can do is that when you don't know exactly how to write the code and you just have an idea, you send a request for comments. And then others will help you write the code. And then there is also a documentation for how to write documentation, which is awesome. Now, let's have a look on how you actually start. If you're the first time when you're contributing, I think the best way is to find a small issue or a small bug that you can send and just to get familiar with the entire process. The compilation of the code, the sending of the pull request. And one good place to start is in the issue tab in GitHub, there is a label named good first issue. Then you also need to read the coding style document, which is similar with the Linux kernel one, and it has a similar tool for checking if the coding style is compliant. This is named checkpatch.pl, and you can, you should run it every time you send the code. Now, another important message, and no one tells you, is that in order to get your patch accepted faster, you need to make the reviewer's life easy. So one of the things is to write a good commit message. And another trick that you can do is to look in the Git history around that area that you are adding code, how others wrote the commit messages and get some inspiration from there. Right? So once you have everything, you can start the creation of the pull request. From my experience, the pull request shouldn't contain more than 5 patches. When it contains more than 5 patches, it means that there's a lot of mental effort for the reviewers to go through all of your patches. So better split it in up to 5 patches, and each patch should contain a logical change, right? And even, so for example, if you have a complex application that you want to add support with a board, just first add the support for the initial board with Hello World, and then on top of that, you may add the drivers in another pull request, and on top of that, you can actually add your application. Right? This helps the reviewer and helps you gain trust, that community gains trust, and that you are following the rules. Now, another thing after you send the pull request, just follow for the updates and answer to the comments. Don't just ignore some of them. If you don't agree with some of the content, you even can discuss with the reviewer on Discord or have the communication on GitHub, but never leave anything that's not resolved until you send the next iteration of the patches. And another thing that I do once I submit the next version is I write a small change log so that the reviewer can remember what happened 2 weeks ago, or when's the next iteration of that. Right, so this is how a simple pull request looks like. For the initial support for ADSP, it just has 2 patches, one that introduces the initial SOC support and the other one that adds the board support. And that's all for now. After you send the pull request, just be patient. Sometimes maintainers are busy, sometimes they delay your pull request because they have other things more important. Now, the general rule is that the assignee from GitHub should review your code or should give you approved, and you should find another one, so you should have at least 2 reviewed bys. Right? Now, as some generic conduct that could work is that after 1 week of inactivity, you can ping the assignee or you can tag them on GitHub. And after another week, you can look on the PR help sub-channel on Discord and ask for help there. There is also a page, but I think this is mostly for maintainers, which they can see the status of the page, of the pull request, and there is a rule that at least 2 days should pass until the pull request get merged. With this time, people can, CI can run, people can have time to look at it. But this happens and works for trivial pull requests. For more complex pull requests, even if this is only the initial support, you should expect around 2 weeks until your change gets merged. So the rule is that you need to be patient. Right? Now, let's see some final thoughts and a sketch of a timeline. If you need to add the toolchain support, then your plans will be delayed a little bit. Your pull request will be delayed by the how fast the new release of the Zephyr SDK is released. So you should budget for this at least 1 month. At least 1 month, but in this 1 month you can start working on the actual board support and you can interact with the maintainers, but the pull request won't be accepted once the CI compiles your code and eventually runs on small tests. Right, so you should expect around 4 weeks for this, and then 1 week for CI integration, because it's not that easy. You need to modify some file in CIs, and then you need to make sure that nothing breaks, because there is a new version of the SDK. And around the 5th week, you can expect some of your pull requests to get merged. And then you add the drivers, and then you add the other things that you need to add there. So basically, this is my experience with Zephyr community. It's a very welcoming community, and people are willing to help you. But this also means that you need to address the comments every time and do your work, right? So if you have any questions, or feel free to get in touch on my email. Thank you. We still have around 4 minutes. You can try this one.
Speak loudly then.
Ah, okay.
I'm just going to bring a mic, but the mic's not working.
Oh, I have another one here. You can try this one. I'm not sure how to turn it on, but.
There's a little tiny switch on.
Oh.
Hello.
Yeah, it works.
Okay. I was just wondering if you're going to add any more boards, support other boards to
Yeah.
Zephyr.
Yep,
You're
yep.
planning to?
Definitely, yeah. This is only, we've seen here the Hi-Fi 4 on 8MP AVK. I'm having a pull request in review for the i.MX RT685.
Okay.
And we already have support for all the boards that have a DSP from MPU families of NXP.
Cool. Okay.
Right.
That's all I wanted to know.
Yeah,
Thank you.
thank you.
Anybody else?
A very simple question. What's the like Git workflow that's involved with Zephyr? Like you have the option to like rebase the commits that you've made. You can merge them. You know, what's standard when you're actually contributing?
Yeah, standard is start from main branch, create your branch where you add the changes, then you push the changes on your fork of the repo, and from there you create a pull request. Next time, when you add modification, if you're in luck, then your pull request will get merged, and that's done for you. Next time when you add modification, you just rebase your changes and force push them on your repo, and the pull request will be automatically updated. This is the basic Git flow that GitHub allows.
Well, so I guess what I'm asking is, should I be careful and make sure that my individual commits that are as part of the pull request are like individually acceptable,
Yes.
Individually buildable,
Yes.
you know,
Yes,
functional all independently?
That's a hard yes.
Okay. Thank you.
It will check each commit.
Yeah.
Yeah, this Zephyr project's one of their big driving factors is to have a very clean history, very clean, so that you'll have reviewers that will look at your commit history to make sure they make sense, which is what he was saying before.
And because you don't want to break the bisectability, right?
Yeah, bisectability.
Bisectability. Once you have a problem, this can save you. And once you have a problem and you see that one commit doesn't compile, then you'll be very upset.
Follow up then, so you mentioned that the CI runs against each individual commit that's part of a pull request.
Yeah.
What other CI is there? Like what checks is it actually performing when it's running it?
So there is some basic compilation. There is some basic static checkers like check patch. I'm not sure if we have more complex checks. we have git lint, which checks that your commit follows some rules, like it has some prefix with the area of the commit. It does actually has some messaging. You cannot just submit empty commits, and some basic stuff. And then we have a set of tests that run. I'm not sure if they are run actually on the hardware or only we have QEMU-based tests there.
Okay. If there's no other questions, then thank you very much.
Thank you.
Test, test.
Okay, then I'll take this one. He doesn't need this
Yeah,
one.
he doesn't.
Great. Thank you. I think I'm all set now. I think I have all the info I need. Thank you.
Clean up my space.
Sure, no worries. No rush. All right.
now.
Can you hear me? Yep, perfect.
All right, all good.
Very good. Probably so, but it's okay. Okay. Can you hear me all right? Okay. Let's go ahead and get started. So, hey, y'all. My name is Daniel DeGrasse, and welcome to my presentation on the Flexboard. This is about the process of developing Zephyr on a keyboard that runs it. So, first off, who am I? So, I'm an embedded engineer at NXP. I maintain the disk and SD host controller code, as well as more recently the MIPI DBI subsystem. I'm focused kind of on displays and video applications. Beyond that, I've been doing some stuff with clocks recently. I have a presentation on that later this week if you want to come argue with me. Beyond, I'm just generally active in NXP upstream. And the reason I want to point this all out is, this is a keyboard. This is more of a product. So why'd I build this? It's a fun challenge, frankly. It's just fun to fool with, and honestly, it's product design without the pressure. I'm using this, and a good friend of mine from school worked on this with me. So it's 2 people we have to make it work with. And if it doesn't work, I have 1 person coming to me for help, and I can tell them that I'm busy. So beyond this, we had some specific design requirements. So I wanted to build a keyboard that was, I'm going to call it normal. I wanted to build a keyboard that was 110 keys about. My friend James wanted to build a 145 key keyboard. For those counting home, normal keyboards don't have 145 keys. This is the keyboard layout and a screenshot of it. If you are asking what M1, M2, what those are for, he doesn't know, I don't know, no one really knows what he wants them for. But he wanted to build it. I thought it'd be fun, so I said, okay, let's do it. Beyond that, we wanted to do individual under-key backlighting because we're all nerds. Lights make us happy. Fundamentally, if it blinks, I like it. So with these design requirements, we went ahead and got started with the process of putting the keyboard together. So the first thing to deal with was component selection process. This was a long-term project because I have a full-time job, and this is something I do when I want to. We started it during the chip shortage, and that was fun, a cool process, but we ended up going with a K22. A couple of reasons. One, it's NXP. Frankly, I work for NXP. If I'm too confused, I do know the system engineers. They might not help, but I can certainly try. And I know the part. I'm familiar with the Kinetis series. It's a pretty standard MCU. It has USB support. We need that for a keyboard, 120 MHz core clock. We picked one initially with a high pin count because in the initial rev of this, we wanted to drive the LEDs with the MCU itself. It turns out, for anyone trying to do this, that is a bad idea. Your LEDs will draw more current the more you turn on. They'll get dim, and then you have a whole bunch of logic managing this on the MCU side that, frankly, bogs down your keyboard scanning rate. So we ended up getting a custom LED controller for this. And that's where the first software support comes in. We picked the Kinetis K22 because it was an entry part. It's supported. That's fine. There's no existing support for this controller entry. I honestly was like, fine, I'll write a driver. That's not going to be that big a deal, and it'll be fun, right? So we picked this controller out. There were similar drivers entry, so I wasn't too worried. I could use those as an example to get started. From there, this will go through kind of fast because I am no mechanical engineer, and I can only design a PCB when forced. So, we're going to go through it quick just to give you an idea of what this looks like. So this is the first PCB that I did for this. It's called FlexEval. This is kind of a fun little evaluation kit because I wanted to, 1, make sure bring up was fine, and 2, I wanted to make sure that the LED controller could do what we thought it would. So this is just a simple validation that I shipped, I think it was $5 on JLC PCB. So shout out to them. Remarkably cheap. And we brought up Zephyr on this thing initially. It was also great, I realized further on, because when you are developing features for your keyboard and they don't work, it's kind of a catch-22 if your keyboard crashes. You can't really keep debugging. So this was kind of the development platform once I got started with the keyboard, right? And this part was kind of how we started doing the bring up. And this is the board itself. So FlexBoard, I haven't touched on this name. It's kind of weird. Why? If you look at these dotted lines, the idea for this keyboard PCB is we only wanted to ship 1 PCB, so they're cut lines. Essentially, you can slice this PCB to one of 2 sizes. You can slice it down to a standard layout. I think no one's tried it, but it should theoretically work as 10 keyless without the numpad. And you can, solder up your keys and use it from there. From there, we just put a flat flexible cable footprint on there if we want to do future expansion. This is a reference, a nice cheap Dell keyboard. The reason I put it here is to give you an idea of the size of this thing, because the full layout PCB is huge, and it's really funny. So yeah, that's the PCB design. Beyond that, the case. Again, touching on this quickly. We did the case custom. Again, it's fun. There's 2 cases, and my friend explicitly requested that I mention the full-sized seal case because it is a marvel of engineering. It weighs, I actually think the fully assembled full-size thing is like 20 pounds. It's full steel. It's incredibly heavy. I've told him, I think if you dropped the case, the PCB would break before the case did. It's very impressive. I had smaller aspirations. I wanted to be able to carry it for one. So I did a smaller case with wood and aluminum siding, and he complained at me and told me I was a bad mechanical engineer, and I accept that. I'm not a mechanical engineer, and that's okay. So we did the 2 cases, and now we made it through the mechanical stuff, and we can talk about the software, the fun stuff, right? So porting Zephyr. So I got this PCB. I told myself, the SDK is scary and bad. I'm putting Zephyr on this to start. We're porting Zephyr from the get-go, mostly because I thought it'd be fun. So to get started with porting, I did the bringer process, right? First off, I just set up an out-of-tree board definition and a manifest repository with Wes. For anyone that's not aware of this, the way that I did this process was, this is, a one-off application, and something I want to highlight here, right? This is kind of the learning process for me, because I develop upstream. Fundamentally, my job is to make things work on Zephyr main and to backport stuff periodically. But for the most part, I work with the latest version of Zephyr. But for this, I'm doing something closer to an application. I have to start thinking a little bit like an application developer, not one with all the requirements of a full-time application developer, but I have to start thinking about all the problems that you encounter. So the first thing was, I didn't really want to pull down everybody's HAL, everybody's abstraction layers, everyone's modules. So manifest repository, what this allowed me to do was basically just say, I'm pulling down NXP's hardware abstraction layer, I'm pulling down Zephyr, I'm pulling down MCU boot because I'm going to use that as my bootloader, and then that's what I need. That's what I need from Zephyr. So from there, with that out-of-tree board definition and that manifest repository, I'm pulling down exactly what I need, pretty much nothing more. And I got a simple board definition and put in UART GPIO pins, put a loop during early init. For anyone doing bring up, the way I did this was just a loop in assembly. Another way to do this, if you have an ARM platform, there's a hook function called ZARM platform init, I think off the top of my head, that you can put a loop in. The reason I did this was I just wanted to make sure if I had some issue with my PCB that I didn't realize that would show up late in the init code, I wouldn't have bricked the board, right? I could potentially debug it later, because I've had that happen to me before, and it sucked. And you've read ahead. I had a build error at the SoC level. What's going on? This is an entry SoC. So, take 2. This is not the same K22 as the one that's entry. So we're doing a basic little SoC port. Brendan's got a confused face. So the first clue here, this has a slightly different set of clock control registers. It turns out we're doing a basic but existent SoC support, and this brought up some interesting questions for me. Because out-of-tree support SoCs are supported in Zephyr. You can have an out-of-tree SoC, but almost everything here is in tree. It's generally a K22. I don't really want to copy all the support files and pull that out of tree, but those are my options. I copy the support files or I modify Zephyr. So that was the first question. Am I going to fork Zephyr? Ideally, I don't want to. I want to track upstream. But the second problem I run into is that you need new register definitions for this part, because it's, again, a slightly different version of the K22. And since there's no way to extend the HAL of NXP's HAL, I went ahead and forked it. So at this point, I did a fork of Zephyr and of NXP. The reason I want to highlight that, right, it's something to be aware of. In my opinion, forks mean that now contributions are harder to make upstream. That's technical debt you don't want to have get introduced. And because of that register, I'm forking. So from there, now that I've forked, I'm going to do bring up on a downstream fork and then send stuff upstream as I go, right? I patched this entry support. It was as simple as grabbing a definition from the SDK, and from there, we're good to go. It's booting. There was one more snag that's worth noting. Not that anyone will run into this, because this part is, by NXP, officially no longer supported, and you shouldn't buy it. Please don't. But, well, unless you designed with it, I should say, right, Brendan? So, USB did not work. It turns out this part has a MPU controller. That's not present on the standard K22. Once we got all this working, I had a brought up basic board. I had this Flex Eval board brought up. I was confident I could get Zephyr running on the full keyboard. So now let's look at driver development. There were 2 drivers for this. Didn't mention this earlier. I put a temperature sensor on there, mostly for fun, and also because once I was done with this board, I figured I'd want something to use it for. I don't know, maybe we use it as a temperature monitor, right? that was a relatively easy driver to do. Upstreaming here was pretty painless. Maureen told me a few things I did not know about the sensor framework, so thank you to her. And from there, it merged. There was a little more difficulty with the LED controller. The reason here was that part of the reason I bought this controller specifically was it supported this thing called auto breathe mode. So basically, this controller, it's an individual LED controller. It drives a whole matrix of LEDs and has individual control on each LED. It can also automatically, via registers you program, kind of do an on-off glowing animation, which for anyone who has mechanical keyboards, we like that. We love glowing animations. And I wanted support for this, but Zephyr's LED API has nothing like this. There's a API call to blink an LED with a discrete on and off time, but there's nothing for a pattern. There is something like this in Linux. There's nothing like it in Zephyr to set up a pattern with intervals and on and off times and things like that. So that wasn't upstreamable, and the rest of the drivers merged. What I ended up doing, I had a conversation with the maintainer, and what we arrived at is either we could do this generically or I could just drop the feature. And I ended up dropping the feature. The thing I want to highlight here, another learning point for upstream stuff, someone might want that besides me, right? And if they want it, they're going to have to pull my forked driver. But, this is just something that I kind of became aware of here. Like, I didn't, I upstream the driver without this feature, but I downstream use the driver with this feature in it. I use a forked version of the driver because I think something I wasn't really realizing before this. If you, as an upstream maintainer, say, you can't do this, someone shipping a product, they're probably just going to do it downstream. They're not just going to say, oh, shucks, bummer, I can't enable this. And it's another point where you're kind of forcing someone to fork. Another thing I wanted to highlight here for the community in general, response time was really good. The community turned stuff around a lot faster than I did, frankly, because I was only doing this when I had the time to do it and when I wanted to do it again. And because of that, I was only really getting online to deal with, each PR maybe once or twice a week or less, once a week. And something I realized from that as well, I've tried to be better about it recently, is like if someone's not responding and they're a community member who's kind of just maybe a drive-by contributor, we call them, they're going to send one PR, that's fine. As long as if it takes them a couple of weeks to get merged, that's okay. It's their timeline, not mine. And at the end of the day, I appreciate them sending upstream, right? It's great to do. So now let's talk about ZMK. So the keyboard firmware here, I want to point out David Brown did a whole Rust firmware, which was very impressive. I did not do that. I used ZMK. I used existing firmware here. ZMK, Zephyr Mechanical Keyboard, essentially this is a firmware built on top of Zephyr that enables a mechanical keyboard. It's got this classic stuff you need, the ability to pull and scan a key matrix, a whole bunch of different features you'd need for dealing with keyboard, like special key functionalities, layers. So I've covered some of this already, just as I said, but it has this ability to do behaviors, which is worth noting. This is kind of an interesting case study on how someone's doing a Zephyr application. ZMK uses a device tree to define these behaviors and then configure them, which generally application device tree configuration is something we shy away from, but that's how they're using it. They're using it to do the configuration behaviors, to define each behavior with specifiers, and that's how you put together things like your key map, is via key press behaviors. And what a behavior does is that it essentially handles key events and things like that, and then passes them on as it needs to. One thing that this brings about, because you're using device tree for everything, is if you want to reconfigure, you need to rebuild your entire image. There's no dynamic reconfiguration in ZMK, at least right now that I'm aware of. And that means that you either have to rebuild it, pull down West, get that set up, or they have a GitHub action to do it as well, which kind of reflects the problem that's obviously here, right? Not every single person who can buy and assemble a PCB then wants to download everything and compile their firmware too. Some people just want a binary. So then the initial ZMK port, as I said, it requires device tree definitions for key matrix and key map. This all makes sense. This is hardware and device tree. This is the key map and the key scan driver node for just that simple 4-button PCB I showed. Very straightforward. And then these key bindings, that KP refers to keyboard, key press, and that behavior basically means this is, the key that gets pressed when you press that key in the matrix. From there, I just had to provide the configuration variables to the device tree and kconfig to set this up. Those snippets, you can set a variable basically to find them called zmkconfig. One thing I wanted to point out here that I thought was cool with West, I did not know about this. You can pass in CMake arguments with West. That was super useful here because every build I was doing, I needed the CMake argument to find the specific directory. And I could have dropped that into ZMK somewhere, but it makes more sense to do it as a variable because that's something ZMK expects you to set during your build as an out-of-tree definition. This is just a little about how ZMK works I wanted to highlight here. So there is this kind of key scan worker that gets events from the key scan driver, and that key scan driver that's pulling this GPIO matrix. There's a keyboard designed with kind of this row column matrix. You set a row high, and then you read the column, and if there's a short there, then your key's been pressed. So that event gets issued back to this key scan worker, which then can pass it on to these behavior devices, which turn it around and potentially produce something like a USB human interface device HID event that prints into an HID report that goes to the host. And that's how ZMK deals with this. So it's got a whole event subsystem to deal with this, which was also pretty interesting to look at. They're not using ZBus, but I think that highlights that ZBus is something we probably need to keep focusing on, because if applications are building their own version, we could probably provide something generic, and we are now, right? So now let's talk about animation support. So this was also why I put all those LEDs on this board, because now we can do fun stuff like this. And ZMK currently only has support for something called RGB underglow, basically just a set of RGB LEDs giving a nice underglow effect. We wanted support for per key animations. This is open source software. They already have a pull request. So that was great. I didn't have to write this myself. All credit to the author here. I think it's Ice4J is their name. They implemented this. All I did was port it over. So that was great and really useful to just be able to pull this in and integrate it. It is worth noting this PR has been open a while. It's something kind of that seems like something the ZMK runs in with trouble. They have a lot of contributors and not as many people who can review. But I was able to pull this in, fork ZMK, integrate it into ZMK. And then one thing to point out that is kind of a fun story of things Zephyr does well, this used the LED API to stream data out to those LEDs. So I was not using the LED driver this person was. I don't know what LED driver they were using, but mine worked fine too. That was not the code I had to change. I just had to port this forwards because the PR was a bit out of date, and that was it. So now we've got animation support, and we have these lovely animations we can do on the eval board. There's one more thing I wanted to add. So I mentioned earlier that ZMK doesn't have proper support for configuring a key map dynamically. So this is frankly a problem for me because a couple of things. First off, flashware, to be frank. I don't really want to reflash my image every time that I want to change something on my key layout. That is expensive for the MCU flashware. I mean, I know it's not likely to add up over time, but there's no reason to wear things out. It's inefficient, right? Beyond that, my friend James, I love him. He's a radio engineer. He doesn't use Git. I don't want to ask him to pull this down and compile it every single time. That's a pain. I am happy to teach him device tree. I will teach him device tree, but he shouldn't have to learn device tree to use this firmware, right? He's our customer in this little role-playing experiment, and I'd like him to have a little bit easier of a time. So to implement key map configuration, what I did, and I will point out for anyone using ZMK, you're welcome to pull this from my fork. It's not really upstreamable because it's kind of a hack. But essentially, ZMK is storing everything as devices. And what you can do here is you can set an index for each device. You can essentially assign an ID to every device and then use that as a lookup table. And you can pull the device based on that lookup table at boot time, load it into a key map in RAM, and then every time you get a key press, you look at that key map in RAM, you look at the device that's at that location, and you call the API on that device to handle your specific key press. From there, I needed to add the ability to actually configure this. So to implement support for this, essentially what I did was I used HID feature reports. This is functionality for anyone who's not aware, USB has USB HID, to be specific, has input reports, which is a report coming from an input device like a keyboard, where the host is saying, the host being like your computer, saying, hey, what's new? What key's been pressed? What mouse button has been pressed? Something like that, and the device is responsible for responding. Set reports are going from the host to the device, and feature reports are bidirectional. That's what we need here because we're trying to read data, i.e. our key map, from the device and then set it back. From there, I just had to add in support. The USB stack, and we're still in the legacy USB stack with this implementation, but it provides callbacks for feature reports. So I just implemented support for those callbacks, used the settings subsystem to store data that was coming from the host side tool, and then read that data back out to program my key map. And from there, I wanted to touch kind of on downstream fork maintenance. This is kind of a retrospective slide I wanted to highlight something that I didn't really realize until I started working on this project/easy version of our product. I built this on 3.3 and pulled patches back, and I haven't updated it. And I probably won't. It's a keyboard. It doesn't have Bluetooth. I mean, it could be hacked, but it doesn't need safety certification. If it got hacked, I would not be able to type. And I know there's bad USB and stuff, but at the end of the day, likely I'll patch this with anything I need to, and I'll keep it on 3.3. And I wanted to point that out, right, because I do development upstream. 3.3 is old news to me, but for this specific firmware, that's the version I'm using, and it's the version I'll use unless a feature comes out. For ZMK, I patched it more significantly. I think probably for anyone doing a product on this, they're likely pulling it down since it's MIT licensed, patching it, and then releasing a binary based on a patched version, just because the license allows them to do that, and it makes sense. So this is the final product. Like I said, it runs ZMK 3.3. I'm using MCU USB DFU mode to update the firmware, so it's relatively simple to do that. The only problem is you have to have another keyboard connected, because when you go put it in DFU mode, you lose your keyboard. You can support key map configuration just via a simple USB endpoint and a little C-host program. There's key backlight controls, and these features are things that come with CMK, full in-key rollover, so you can press any number of keys, they'll show up on your system on the other side, and then support for media controls. So then just a little bit of a retrospective I wanted to do with this. The first thing is I think I've seen Nordic actually doing a little bit of this. Carlos, feel free to correct me if I'm wrong, but it seems like Nordic's looking at ways to extend SOCs downstream. And this I think we should look at because it was frankly a little bit annoying. I had to fork Zephyr almost immediately during bring up. It was surprising too. I was like kind of bummed. I was like, shoot, I really wanted to track upstream with this, but at the end of the day, this is a new SOC, and it's not going to make sense to pull all this code out and then try and maintain it release to release. I should probably just patch entry and then try to upstream. And I guess I should note, the SOC is in fact upstream. Like I said, it's legacy, but it is there if you have this and you'd like to use it with Zephyr. Beyond that, I think we should probably look at ways HALs can extend themselves. I know, not to call out an XP, but we have, it's hard to inject a new SOC into our HAL. You can't really just inject into the build flow where you need to put in an out-of-tree SOC definition if that's something you need to do, which it might be, right? There's parts that we don't officially support in our hardware abstraction layer that people probably do use. And I think HALs probably should look at a way to deal with that because, there are probably customers that want that. And like I said earlier, ideally you don't want customers to have to fork your project. Beyond that, ZMK was kind of an interesting example of a downstream application to look at. One thing I noticed, they have now updated to 3.5, Zephyr 3.5, but I was on 3.3 because ZMK was based on 3.3 when I started working on this. That's a little concerning that it takes them, that much time to update. It is, a project that has, I believe, one main maintainer who does a very good job, but that is one person. But I think it's something to consider. Like, is our velocity so fast that this project is having a lot of trouble updating version to version? And if so, do we need to provide better guides? Beyond that, I highlighted this earlier, that it has its own event subsystem. kind of just something I wanted to point out because it's evidence that we should be investing in something like ZBus. We should be investing in an event subsystem for Zephyr because that's something applications are needing. One thing I also wanted to point out, just kind of at the end here, the old man screaming at the clouds about testing. When I initially went to pull down the support for Zephyr, the Kinetis USB driver just did not work with USB DFU mode and hadn't worked for like a release. Kind of just a general question as far as testing that I think we need to look at is USB seems like it frequently slips under the radar as something we test upstream. We find out long after the bug was introduced that in fact USB isn't working, or this specific USB feature isn't working on this platform. Yeah, and that concludes the presentation. If you have any questions or would like to see that shoddy wooden and aluminum case, I have the keyboard up here. So thanks so much. Yeah. All right. Sure. Yeah, you're fine. You're totally fine. Yeah.
Testing. Okay. Thanks, Daniel. That was great. You mentioned that the dynamic configuration feature is not upstreamable.
Yeah.
What do you think it would take to make it upstreamable?
Yeah. Sure. Yeah, that's a good question. I think the main thing that I didn't love about it was the way I'm storing that configuration data into ROM. I don't want to dive into all the details right here, just because I don't know if everyone cares, but I'm happy to show you it after this. Essentially what I'm having to do is I'm having to kind of pick an ID for a device, which is somewhat arbitrary, and then use that like a lookup table. Ideally, we'd have a better way of doing it. The other thing that I think is kind of missing from it is a graphical interface. I don't do GUIs. They scare me, and I don't even like to develop in them. So I think that's honestly something that's missing is, somebody who can write a graphical user interface that's half decent, because I certainly can't. And you need one to make this usable for end users, because we're not all.
Pete Johansson, which is the maintainer of ZMK, he's working on, it's called ZMK Studio right now.
I've been roughly following it. I mean, if there's interest, I'll absolutely submit it upstream. I have no problem submitting it upstream. I just didn't think it was particularly ready. But if there's interest, I will absolutely put it out. I have no problem with that.
All right, thank you.
Yeah.
By the way, checked on that PR in ZMK is not merged yet, the one you used for the animations.
Is it merged now?
No, it's not. It's not. I said that's disappointing.
Yeah, because I'm subscribed to it. I'm still following.
All right, okay.
I was just going to ask, if you were to take a new path, would you do something significantly different?
Oh, yeah. Oh, yeah.
Just curious.
Yeah. I mean, let's see. The MCU is way too high of a pin count. It's just that once I'd done the design, I didn't want to respin the PCB.
Sure.
So I kept it as is. If I was going to do it again, I'd probably use our MCX parts. They're good for this. Or maybe probably an MCX, honestly, because they have dual core. And that's something I'd love to fool with. Because if you have dual core, you can do cool stuff like scanning your keyboard in one core and then sending the USB reports on one other core, because those milliseconds, microseconds even, they really count when you're gaming.
Thanks.
Yeah.
Really interesting project.
Yeah, thank you.
Yeah. So one thing I noticed, you never mentioned JTAG or SWD. So.
Yeah, that's fair. I mean, there's a JTAG and SWD header on there.
I don't, not blaming you, but I look at these dev boards that people are making.
Yeah.
Hundreds, especially like the RP2040, and 1 out of 10 maybe has a JTAG or SWD port on it. And personally, I find that really, really weird.
Yeah.
I mean, what's it like? Because you mentioned also having to put that special thing in there so you wouldn't break your chip and stuff.
Yes.
And that wouldn't be an issue if you had a JTAG port on there. Was any reason?
No, there was a JTAG port. So I put a JTAG port on there.
Okay.
The reason I put that on there is because in college, I was bringing up a TI SoC, and I put the RTOS on there, and the RTOS started using an oscillator that was not on my board, and the board stopped working.
Yeah,
and maybe I could recover it now. I was younger and stupider, and I don't know if I tried everything I could have, but I wasn't interested in finding out if that would brick the board, to be honest with you.
Yeah,
So,
one,
yeah, you're fine.
one thing I learned from the JTAG is you have a JTAG plugged into your keyboard, you're GDB'd into it. Do not press Control-C on that keyboard.
Oh, I know.
Because
Yes.
it sends Control-C
Yes.
and then it repeats forever.
Yes, because what I do when debugging the keyboard is I would comment out the USB HID report code so it didn't send anything back, and then I could debug all I liked. But yeah, if you're debugging your keyboard, that's also why I had the Flex eval board, because I could do that safely. But if you're debugging your keyboard, like you said, and you break in the debugger, and you've sent your key press, it's not going to send the other report that says your key was released, and you're just going to keep sending the key press. And GDB doesn't like that. You can't get out of GDB. You have to unplug the keyboard.
I was just going to make a comment related to that, and then maybe into the guts of a keyboard controller specifically. But with eval boards, I'm from NXP as well. I work with Daniel, for those who don't know. We have a debug probe on them, but even then you can get scenarios where the device will boot up, especially if it has security, and is immediately running the code, and it can be in such a tight loop that it's impossible for the debug code to get control. So I think is the thing to be wary of if you have a super tight loop in there, that you can cause problems for yourself, and you can brick a device that way effectively.
I mean, the hope is that you don't, right? But I learned once, and I don't want to learn again. So.
Yeah, we do have ways on more modern devices where we can use this debug mailbox and erase the flash to recover. But on older parts like K22, I don't think you can do that. I don't know that part.
I don't know of a ROM on K22. No one's told me about one.
It's a very basic ROM. Yeah.
It wasn't going to come off. If it broke, it broke. Yeah. Okay.
All right, just one quick check on, since I was away, if there's any questions on the stream? No? Okay. So any more questions?
Okay.
All right. Thank you very much.
Thank you. Hey.
Hello.
How are you?
I just wanted to
go ahead.
say hello. Introduce myself.
I think I've seen, I have seen you on there. Hold on, where are you doing?
1, 2, check. Check 1, 2, check, check.
That's cool, and I'll give it, if you want, it probably.
I can put it closer.
The top button. So, underneath the top, I'm sorry.
Gotcha. Check 1, 2, check, check.
And I'll make this neat.
Okay.
He's really upset that mine's two-color. I like that it's monochrome LEDs.
Oh, you didn't do.
No, because they're under a key, and you only have 2 holes in the cherry to do.
Because I use RGB, I use the.
Because you use
2012.
Yeah, you have them under the key.
Well, I don't.
Oh no, you have them beside it.
So the first thing I did when I looked at this thing is like, well, if I turn all of these LEDs on, I will use.
Check 1, 2. Could you talk for me just a second?
Check 1, 2. Hello, hello.
But then I got the LEDs on my board.
Talking, talking, talking. That
Awesome,
sounds
perfect.
pretty
Thank you.
good.
You could turn it off and turn it on when you want.
Okay.
That was the same.
Check 1, 2. Check, check. All right. It's 4:20, so we can get started. So first, I'll start by saying thanks to the NXP people who told me about this conference. It's fun to be here since I'm a relatively new sort of, member of the Zephyr community. I became interested in Zephyr about 1.5 years ago now for this particular project. And I'll sort of start off by saying this augmented reality project I'll talk about has kind of been a long-running thing, and I've gone through several prototypes. I'll be talking specifically about one of the more recent designs that I did. So this presentation covers up about until mid-2023 in my prototyping journey on this project. So in this case, my sort of overall augmented reality project has a few major goals. I started it mainly just because I wanted to learn about low-power mobile electronics. I want to try to make something very small and lightweight, which can serve as a wearable computer with a near-eye display. So you'll see photos of this in the slides later, but it's a wearable device. It has a display, various processing capabilities and sensors. So I wanted to try to make this, as close to phone-level display capabilities as I could. I want to try to see, could this be a useful device for showing complex graphical information, perhaps referring to notes, viewing maps as you walk around, and just experiment with those sorts of potential applications. So initially, it's monocular. It has a display for one eye, kind of like Google Glass was initially. It's this sort of lightweight augmented reality idea. Now, in my previous prototypes, I had been using embedded Linux systems. Some of the previous talks I gave years ago about this, I focused on using an MPU from STMicro, that STM32MP1. So I had a design using that. I was trying to sort of achieve these similar goals, and eventually I got sort of frustrated with the MPU approach of doing things and always using embedded Linux. First, I'm always dealing with DRAM power consumption. Having an external memory device with a very fast, complex interface also sort of restricts your board design opportunities, makes it harder to miniaturize. So you end up having to use system-in-package or package-on-package devices to get the design as small as I want it. And of course, this won't be covered in this presentation, but optical design and mechanical design of such a device is a whole world of other engineering challenges. Here I'm mostly focusing on software considerations bringing Zephyr into this project. So when I decided, let me try an iteration of this prototype using one of these crossover MCUs, or at least sort of crossover processor that has been showing up with more advanced multimedia capabilities than traditional MCUs, why would I choose to run Zephyr on it? Well, initially, I want to be able to move as fast as I can in this prototyping process, because being a side project, I always have limited time, and I want to quickly get an idea, what can I make work? What's the farthest I can push this quickly? Where are the points of most resistance? So to me, I was quite happy moving to a Zephyr development workflow from my sort of embedded Linux background. I felt like the whole build, debug infrastructure with West was easy to understand and set up. It's very appealing to have a collection of drivers to refer to so that your job bringing up a new board is easier in a lot of cases, or you have reference code to take a look at. And of course, the community surrounding Zephyr makes it appealing, especially in the long term. If you make progress on some new sort of esoteric element of your system, there's a hope that maybe it could be useful to something else, to someone else in the future. And that kind of connects with the vendor independence aspect as well. That's been mentioned in other presentations today. So first, I'll just give an overview about the particular board we're working with, and then, of course, there's the mechanical enclosure. But this arrived, it was kind of designed late 2022, early 2023. It's 10 millimeters high, so it's this little board. And it essentially integrates, of course, the MCU in the center, which we'll talk about on the next slide, external flash for the code, display and camera connectors, of course, your various oscillators, power management stuff, some sensors, accelerometer, magnetometer, gyroscope, and a Wi-Fi module from Silicon Labs. Of course, there's a lithium polymer battery, single cell that it can charge. In this photo, it's covered by a black cap, but there's a USB Type-C connector on the right-hand side. And for those who might be asking about debug connectivity, so SWD in this case is exposed on sideband use pins of the Type-C connector in a slightly non-spec compliant interpretation of that USB debug accessory concept, which is used in some other commercial products. So the sort of main character of what I'm talking about today is this NXP IMX RT500 crossover processor. So it's a microcontroller with a large internal SRAM. And in this design, that's appealing because you can put it on a really tiny board like this. You get your microcontroller, but you also get MIPI DSI display output, so display controller and a DSI PHY. You actually get a 2D GPU. You also get the Tensilica Fusion F1 DSP, which is, but VLIW DSP with some cool instructions that can be useful for encoding, decoding variable length stuff. So it's appealing just because of this notion, oh, can I take a low-power microcontroller system and push it to do those graphical things that my embedded Linux systems were doing? Can I connect a high-resolution display to it? Could it be useful for this kind of wearable, where I want multimedia and I want low power? So that's the motivation for taking a look at it. So just to get started, before jumping into all of the problems, of course, that I run into bringing up something like this, we'll just start with some of the easier things. So of course, when the board arrives, power it on, connect it to the J-Link, and SWD works right away. So at that point, you can load code into SRAM and execute it from the SRAM on the chip. But if you're going to do a custom board with one of these IMX RT parts, and you have code in external flash, it's likely using this Flex SPI interface, which requires some configuration. So for instance, the eval board uses an octal SPI interface. It uses it in DDR mode. Of course, it uses different clocks compared to the part I have. So first, you're going to need to change this flash config potentially for the flash part that you use on your board. So we'll go back to the dark slides, hardware mode. So of course, take a look at the datasheet for the flash part you have on your board. Things like the sector size, properties of the blocks on the device matter. And while we're in hardware mode here, to get the board initially working in a sort of nice state to move forward, we also want to check a few other things. So the power management IC, the PCA 9420, which is specifically meant for this RT500 part, you can, of course, change properties of the regulators, voltages, and such over I2C. So on my board, sort of to improve routing, everything is on a single I2C bus, which is the Flexcom 1 interface. So we're going to have to check that in the device tree to make sure we can talk to the power management IC, and just get that fundamental thing out of the way. And then on this design, all of the I/O is 1.8 volts. So there are a few things we'll look at there as well. So going back to software mode, in this case, I have the flash config file with the requisite things changed. There are changes in this lookup table mechanism, changes to the clock, and the number of I/O pads used. In the board.c file that comes along with the board directory in Zephyr, for instance, for the eval kit or for your custom board, there are calls to the hardware abstraction layer for things like setting up I/O pad voltage ranges. So kind of step 0, make sure all of these are appropriate for your particular system. And of course, then enabling clocks for things that might not be present on whatever you're using as a reference. So for instance, if you're using peripheral IP or various blocks that don't have their clocks enabled, you have to make sure that that's happening properly when you're talking to the HAL. So those are just a few sort of small details that I just had to pay attention to bringing up a new board for the first time. And then you're free to organize everything nicely in device tree. So from this point, I have a board that can run code from the flash. I can do all the standard easy stuff with devices on the I2C bus. And then it was kind of time to move to the real problem I wanted to see if I could solve here. Can I take this little microcontroller system, drive the display I want with it, which we'll get to next, and see how far we get with these sort of multimedia capabilities in a low power system. So the primary challenge and what I found the most fun about this overall project is this display that I chose to use. So in these little wearable devices, of course, being space constrained, the amount of area you have for the display is also constrained. So this particular display is an OLED on silicon micro display. So it has a silicon backplane and then an active matrix OLED structure on the top. And the pixel density is incredibly high. So these are quite cool devices, also quite niche. There's not a huge amount of applications for them apart from these wearables and sort of emerging devices like that. This one is made by this Chinese company called Vutrix. VTOL6202, I believe, is actually the part number of their backplane and display driver IC that's integrated into the backplane. And then the manufacturing of the entire module is sort of a complex process of multiple other companies that confuse things a bit. But I refer to it as VTOL6202. It has a MIPI DSI interface with either 1 or 2 4-lane links. So you can use one of them or you can use 2 of them, up to 8 lanes total in parallel at the typical about 1 gigabit per second per lane. So that's so that they can do refresh rates higher than 60 hertz if they want and things like that. Some other random details that you find in the datasheet about it, you have to use the 24-bit per pixel packets in high-speed mode. You have to ensure that the clock is discontinuous, so the high-speed clock changes to the low-power mode of the clock lane in the blanking periods. So things like that, I ran into as problems along the way bringing this display up, and you just have to dig through all these tiny details of this, esoteric part and get it right. But that's part of the fun. This particular display runs in video mode, so you're constantly sending frames to it. If you've seen some of the other demos of RT500 low power stuff from NXP, one of the tricks that you can use is put a lot of the chip into a deep sleep state where just SRAM is retained and clocks are gated, power is gated, and so on in between display frames if your display can maintain its own image, but between those frame updates. For instance, if you only update the display once per second. In this case, you unfortunately can't do that, or at least I don't believe that this display has any capability to do that internal memory sort of behavior. But in any case, just getting started with bringing up this display, well, the RT500 MIPI DSI PHY only has 2 lanes, so we have to figure out, can this display even support being driven by a 2-data lane DSI interface. The clock, according to the documentation, is limited to less than this 1 gigabit per second per lane that we might be accustomed to with most of the standard MIPI DSI implementations. And of course, what sort of frame buffers can fit in the onboard SRAM. Because on this particular board, I don't have external memory, like external PSRAM that they have on the eval board, and that's mostly to save board space. So I'm working with a certain set of constraints here, but I found that kind of fun just in the sense of seeing what can you do with limited resources. I find it forces me to learn about all the details in order to get things right. So there are a few points in our favor about getting this display to work. First of all, you can actually run the MIPI DPHY faster than specified in the documentation. It works at room temperature. Maybe you shouldn't do that if you're more serious, but I like to see what works. The actual display itself actually has registers which can select a smaller region of pixels to refresh. So this is cool because if you're viewing the real world and trying to display some sort of overlay, as an augmented reality device does, most of the pixels of your display will be black, because black means, well, you're looking through to the real world. There's no extra light presented to the eye. So you could just say, oh, let me display a small image in some region of the display. I only need to write that much data out to the display. And then using registers on the display, you can tell the driver IC in the backplane to move that region of refreshed pixels around the display. So that's a neat trick that could also be used in an application like this. If you were constrained in terms of the DSI interface and you wanted to use fewer than the full 1920 by 1080 pixel display. Now, in terms of fitting buffers in the SRAM, you can fit an individual full HD frame buffer at 16 bits per pixel. Of course, with all of these, yes, you're restricting the amount of SRAM you have available for other things. But again, this is just what's possible if you push the limits. You can fit two 1080 by 1080 square frame buffers. And of course, if you were to use sort of YUV modes or 12-bit per pixel NV12-like pixel formats, which aren't yet supported in the Zephyr drivers for this particular display controller, you could get it down to 12 bits per pixel and maybe push it a little farther. The actual PHY, can fit. If you do that 1080 by 1080 square, you can get over 60 hertz out if you're using the slightly higher than recommended PHY clock, and around 60, 65 hertz if you do this reduced refresh area of the display. So this is kind of promising, because it means, there's still things I can do. It's not sort of hopeless to get this, fancy little obscure display to work with this microcontroller, even though perhaps if you just take one glance at specs and data sheets, it might seem so that it might be a very a poor fit, but it's possible. So there are more problems. As you can see in the photo, it does work, but before you get to it working, there are more problems. This particular display, of course, there's almost no documentation about it. You have to write this gigantic set of initial settings to registers. Some of them are lookup tables for things like gamma correction, color correction, various brightness curves, and essentially none of them are documented. The sellers of this display and the manufacturer will just give you this blob of writes to do using display command set in the low power mode of the MIPI DSI interface. And they say you have to use the hex 39 packet type, which is the display command set long write, to do all of these register writes. Now, typically you wouldn't do that. Typically you would sometimes use the short writes, but they want you to do them all using this long write. And that actually doesn't work in NXP's HAL because it breaks if you try to do a write with only 2 bytes using the long write packet format. It's actually easy to fix. It's just like one-liner change. But this took me like a month of free time to debug because I'm learning about this for the first time as I debug it. And in the scope trace here, you can see this is, data lane 0 in low power mode, so it uses this, sort of one-hot encoding. So it ends up treating the 2 bytes of data as the length, and then just, reads tons of memory, dumping it out because it thinks it's writing something super long, a super long payload. So once you fix this, then the display works. So it's very, very exciting to see this work for the first time. And I kind of just enjoy doing things like this because, then when you take a look at a, normal, not terribly, terribly obscure MIPI DSI system or display, then it feels easy after dealing with things like this. So I found it a fun way to learn. So that takes care of display, and I mean, you can see a little bit of interesting graphics on that disassembled photo of my device over there. The next thing that I wanted to check was, can I easily bring up a camera? So apart from the display connector, there's another of these little FPC mezzanine connectors for a display, which the one I chose is from Himax, the HM01B0, which is just a low resolution, like 320 by 320 sensor meant for always on applications. So this has one of these parallel interfaces, which you might have seen before, where there's 8 bits of parallel data out, it's clocked, there are horizontal and vertical sync signals. So if you read the datasheet for the RT500, it says, yeah, sure, you can connect this kind of parallel interface to FlexIO. And FlexIO is this cool peripheral with sort of shift registers that can be cascaded to form a sort of buffer. And then to get this data into or out of the FlexIO, of course you want to use DMA. So there's this smart DMA engine provided in the chip. So you think, okay, of course, this should work, right? This should be fun. Now the smart DMA has APIs that from Zephyr you can call to do various high-level things. So for instance, smart DMA is used a lot on this chip to move data from memory to the DSI interface or to other displays instead of the sort of more standard LCDIF display controller. But in this case, I want to go the other way, right? I want to use this smart DMA to read data in from the FlexIO to support this camera. So it doesn't have a high-level API for that. But it's a DMA engine, right? We should be able to make it do that. Well, there's actually a lot more to learn about what smart DMA is, and it's not quite as simple as just treating it like a DMA engine. So I found out smart DMA is actually this 32-bit programmable I/O processor, and it's designed to do things like keypad scanning, encoders, these sorts of fast I/O protocol decoding and things like that. In other places, it's called EZH. I found that name more, so I started calling it that. So really, I got into this, because, well, this is an obstacle standing in the way of me getting my system to work, right? So the display was quite nice and straightforward experience for the most part. This is a bit trickier. So in typical situations, a programmer just uses the APIs that the smart DMA engine firmware exposes. So there's a binary firmware blob that's loaded onto this smart DMA engine. The Zephyr driver says, okay, the user wants to use this particular API, which might be this, for instance, DMA endian swap. All of these, for instance, are moving data from memory to a display, or doing, actually some of them are memory to memory, like there's pixel format conversions and whatnot. But generally, you're only supposed to use these predefined APIs. If you want to do something else, like read data from a camera, which in 2023, when I was doing this, was not available in the binary blob. If you want to do something else like that, you're out of luck if you're a standard programmer. So, of course, I'm new to the Zephyr community, but in contrast to things like the display system, where I felt I had both a nice, comfortable level of abstraction and a good view of what the hardware was doing, here it seems like what you see if you only look at Zephyr is a far cry from what's actually happening in the hardware. If you only looked at Zephyr, you would think maybe these APIs are actually implemented, maybe they're fixed function in the hardware. They're not. There's actually a firmware, and it is programmable, but the programmability isn't exposed to users at this point. So of course, Going farther and further off topic from making an augmented reality device, I wrote a disassembler for the EZH instruction set. So you take this binary blob and, I've always liked to take things apart and know how they work, so I had to know how this works. So you can download the PDF of the slides if you want to look at the comments for a longer period of time. But this is my interpretation of how this endian swap thing happens, and generally what I think is going on. So if you wanted to do something custom with this processor, there's actually a header, FSL Smart DMA PRV.h, which you can use to essentially assemble these sorts of instructions back into binary just by compiling it, because they're like macros, essentially, which are defined in that header. So this is what you have to do to get this camera working on this board, right? So that's kind of an example of one part of this development process which wasn't as quick or as low resistance to getting this sort of system up and running with Zephyr, because you have all the niceties of Zephyr, but then you have mechanisms like this under the hood, which can stand in the way of this sort of system being simple and easy to bring up. So more recently, I haven't gone all the way to having examples of code of my own that actually runs on this processor, because this particular camera, HM01B0, can actually output a serial stream just like normal SPI, and you can just go back to that if you just want your frame data and you don't want to deal with this FlexIO, because then you just feed it into a normal SPI peripheral, use standard DMA, and you're done. So with these low resolution cameras, you can do that. But sometimes these sorts of mechanisms can be troublesome. So in terms of the overall project, these are just some photos of this sort of mechanical assembly. In this enclosure, this board, is in one side of the enclosure, essentially, and then there's room for the battery in the other side. Currently, of course, optical design being a big challenge, this just uses a very simple optical system with 2 biconvex lenses so that the display is focused correctly kind of beside your nose for the right eye. So it was, an interesting sort of journey. I find it always an interesting journey to go all the way from, designing a board to doing, software bring up and then doing the best I can with my mechanical design and limited optical engineering skills. So then in terms of what can I do with this system? Well, apart from using the display and moving about within the limited camera functionality we get without being able to program EZH ourselves, there are some other fun things. Of course, since the board has accelerometer, magnetometer, and gyroscope, you can do sensor fusion nicely and get the orientation of the user's head. So that's often a pretty fundamental thing in augmented reality and virtual reality applications. I also experimented a bit in the past with, using accelerometer data to detect, the user tapping on the device, which could be used as an input method, and of course, looking around forms of, an input method to change what is shown on the screen. For connectivity, this Wi-Fi module I have on board from Silicon Labs, someone had a pretty well developed driver which wasn't merged yet. I haven't checked on the status recently, but it wasn't too difficult to get Wi-Fi running and use Zephyr's network stack to connect, in this case, to an Android phone. I used using Wi-Fi Direct, and then do fun things like shuttling data back and forth, showing content from the Android phone screen on my wearable device's screen. I did a sort of very simple video codec just to get that working, sort of minimum viable, which just takes into account things like solid filled areas, scrolled content, so you only send what's new and cases like that. Big areas where I think more progress could be made. This chip, of course, in addition to the Cortex M33, has the Tensilica Fusion F1 DSP. So it has quite a few fun instructions for variable length decode and encode. So I think you could implement some nice sort of coprocessor functionality on that for handling data compression and decompression if you're sending sensor data off the device or receiving video data wirelessly to the device. So that might be a fun way to learn about interprocessor communication with the sort of mailbox mechanism and Zephyr's support for that. The other fun thing on this chip would be the GPU, which I haven't really looked at yet. But in a lot of these sorts of applications, if you, for instance, render a frame on a device like your phone, then you transport it to the wearable device, by the time it's received and decoded on the wearable, the user's head position may have changed. So then, for instance, you could use the GPU to warp the image accordingly for the newest data that you have on board from the inertial measurement, your accelerometer and gyroscope. So that's a pretty common thing in these VR, AR wearable applications. Of course, designing optics is a big area in which I'm still learning. And there might be some potential to do display systems with 2 displays, one for each eye. But I don't have content about that yet at the moment. So kind of in summary, hopefully this kind of sums up my experiences using Zephyr to try to make progress on this very ambitious long-term AR project. So some systems on this board are very easy to get going with Zephyr. Of course, when you're initially bringing things up, you have sensors like these inertial sensors that have existing drivers. It's very easy and convenient to get those going. Things like the display, take some digging, but I think Zephyr provides a good framework in which to do that digging. I found it really enjoyable to learn about, new aspects of maybe DSI I didn't know anything about before, using Zephyr as a tool to develop this system. The, I think, biggest takeaway that I feel like became clearer in my mind working on this system is that in a lot of cases, specialized peripherals are very important in getting the most out of your silicon. In this case, if you have some very nice specialized peripheral which can do exactly what you want without burdening the CPU, well, yes, it's very convenient, but only if you're able to utilize it. So in the case of the EZH or Smart DMA, well, it's not going to help you if you can't program it. So in a lot of cases, users do want a simple picture, because if they're doing something simple, they don't want to think about all these details. But advanced users then can't get the most out of their hardware if the advanced features are hidden down in the HAL, behind a binary blob, and so on. So I think those sorts of considerations could potentially become more important in the future. I know in some cases, new AI or ML accelerators will have one or even multiple dedicated sort of management processor units running a firmware in order to schedule things onto execution units, and in these AI and ML workloads, well, you could just take a high-level model and say, yes, please run it on the hardware, but then perhaps in some cases you want much more fine-grained control over what this embedded management processor is doing. So that's, I think, just something that at least I think I'm thinking about into the future. What's the best way to expose these sorts of complicated, dedicated hardware peripherals to users from a software point of view? Because they seem to be showing up more and more. Things like this EZH or dedicated coprocessor peripherals with sort of specialized abilities. So that kind of sums everything up. I know it could potentially be a lot of content and disjointed, complex content from many different avenues of this project. But if you have any questions, I'd be happy to answer them. Thank you, yeah.
First of all, people like you inspire me. I love that you've gone in and dug in this deep. Is there a sort of an open group, a team working on this as well? And if so, how do you sort of engage with them? How do you keep the whole thing going as a group?
So this project has just been my personal project. Really, I was working on it in college just as a side project. And this particular iteration of the prototyping I mostly did, senior year of college. So in terms of like software development in Zephyr, there have been a few, patches and pull requests I contributed back so far to fix minor things with this, but there isn't a group of other people working on this project along with me right now. Of course, the broader Zephyr community has really helped make things like this possible. Like for instance, the display drivers and various things like that showing up at just about the right time for me to start using them in early 2023. But I don't have like any direct collaborators on this particular bit of hardware right now.
Thank you.
Two questions. First one is, in one of your slides, you have a big asterisk saying there's a long story on how you figured out all these documented register settings. Could you go a little bit more into that? And the second question is that you designed the board before working out all the numbers on whether you can like actually make everything work, or you kind of have a good idea on that, like it would kind of work before? So yeah.
Okay, yeah, so I'll answer the second question first. So when I designed the board, let's see, I designed and fabricated the board without knowing how to configure the display for 2-lane MIPI DSI mode. So yes, I took a risk in fabricating this board that the display would not work at all, because this particular register setting that's hard to find for this display, if it didn't exist, the multiplexing of data over the lanes wouldn't be correct. You can't just connect 2 data lanes and have it work. So yeah, I essentially did fabricate the board before having everything figured out. Things like what you can fit over the interface, I think I had checked on that briefly. I hadn't really, looked into it in detail and done all the fiddling with, resolutions and blanking that the display is happy with. So yeah, I try to make myself take more risks with designs because I feel like they work too often. Yeah. And in terms of like the long story, so a lot of it is, me emailing back and forth with various Chinese sellers who are selling these displays, trying to figure out, who knows about the actual display driver IC on the backplane. So there was a bunch of reverse engineering I also did about the registers. This was in like end of summer 2022. I was like fiddling around with the registers of this display, dumping them all out. There's a company, Novatech, which makes display driver IC IP blocks that go into display driver chips. And some of the registers have some similarities to what you can find in Novatech datasheets publicly. And then there's some article, I forgot where it was. There's some reference somewhere on the internet to this company, Viewtrix, having some dispute with Novatech. So it seems like it may be similar to some of the display driver ICs from Novatech, but it doesn't match up exactly with them. Like there's stuff in these big initial register settings that they'll give you that isn't anywhere in Novatech datasheets. So I don't have documentation for it. I just happened to find someone who would tell me what register to set. Like, they didn't give me a data sheet. They just told me set this register to this value. So yeah, it was a long journey, but I suppose part of the moral of the story is it helps to get better at talking to people.
Thanks for the great talk. And I'm just wondering how many revisions did that board require, and also were there any lessons that you learned from designing such a small board that packed, everything on it?
So this particular sort of long and narrow board, I've done 2 revisions. So the initial one and then a second revision. It was just to fix a few minor things related to this Wi-Fi module. Everything like display and all the sort of basic stuff worked on this first iteration. So this was sort of the first board I did, which is so tiny that you have to use high density interconnect stuff like blind microvias. So it's the first board I designed with those sorts of techniques. But it's not being hand assembled by me, of course, because I find it takes too long for me to try to do that. So it's my exposure to like the assembly considerations is limited because of course I just design it on the computer and it shows up at my door. Of course, yeah, there are a ton of new board design techniques I learned by doing this sort of thing. And though this presentation was of course focused on software, that's a significant motivation for me to do this project as well. Yes, it's just to learn about more modern PCB design techniques and microelectronics details.
So you had some objectives on your project about low power and stuff like that. So how did you get to the point of trying to, one, measure, but then figure out how you can tweak things, or especially with respect to what Zephyr may provide to you and also this part that you were using?
So yeah, I have done power measurements on this system. I don't have them sort of collected in a nice format to present. Essentially, if you have the display on at reasonable brightnesses so that it would be viewable outdoors or in bright overhead lighting, the display power consumption quickly dominates the overall power consumption of the system. The other thing, which is really sort of a major contributor if you're sending lots of data, is Wi-Fi, especially if you're transmitting. The actual MCU, of course, while there are a lot of techniques you could use to save power in sleep and various things, simply decreasing your display brightness, saves you more power. So I didn't go super deep into looking at that yet. I'm sure there are some savings to be made there, but for instance, if you were able to sort of compress things more effectively and send less data wirelessly, I think that could potentially have a larger impact. So yeah, I haven't gone very deep into looking at that yet. I suppose a contributor to not spending a ton of time on that yet is the fact that with this display, I have to refresh it all the time, so the part can't be put into the deep sleep with SRAM retention. But you could power some other things down probably.
So thanks for the talk. This is really cool stuff, honestly. Did you, with the display, was this kind of the only display that could do it, or did you look for a display that could do command mode so you could get away with going into low power modes like that?
I haven't seen one of these OLED micro displays with like internal frame buffer memory. Maybe they exist. I haven't found one. Apart from like this particular series of displays from this company, Sony also makes a lot of these micro displays, but they use the LVDS or FPD link interface, which is not maybe DSI, of course. So it would not really be possible or easy to use them with this MCU. So yeah, currently this display is really one of the only options that kind of fits what I want to do here in terms of its size and resolution.
Was just wondering, with the smart DMA engine, are these binary blobs just being handed down from on high in NXP, or is there actually some sort of compiler where, users can generate their own things? Is this kind of an NXP or a Zephyr issue?
They're just handed down from NXP. Yeah, so I suppose the question that comes up is perhaps how should Zephyr deal with situations like this, which is a question for the more experienced people than me. Yeah.
Questions? Yeah. One other question for you on the wireless part. So I sniffed around and looked. It looks like the pull request is using SPI for that. Did you look at switching it to SDIO? Because I know there's SDIO on there, but I'm assuming you built it out over SPI and you're locked in now, right?
Right, yeah. So on this board, I only have SPI connected, yes. Of course, yeah, SDIO would be more ideal in terms of getting it faster. But yeah, for this module, I only did SPI.
Thanks.
Any more questions? No? Well, thank you very much. Thank you.
Thank you.